Ever wanted to build your very own face detection model? Well, in this video, we're going to be doing exactly that using a deep object detection model. Ready to do it? Let's get to it. What's happening, guys? My name is Nicholas Renault, and in this tutorial we are going to be doing exactly what I said at the start, building our very own face detection model. Now, the cool thing about this is that it is actually based on an object detection architecture. So if you wanted to go and use this for something else, maybe detecting different types of objects, you'd actually be able to use this pipeline to do exactly that. Now, in this tutorial, we're going to be going through a bunch of stuff, and as per usual, we're going to be doing it with a client and developer relationship, so you're going to see the client conversations as we go through it. But specifically, we are first up going to start out by collecting a bunch of images using OpenCV and labeling them using a new library called Label Me. But the real kicker is we are going to be performing image augmentation. So we're going to be using a different library for that, and I'm going to talk about that a little bit later in section 2. We're going to annotate it and then build up our deep learning model from scratch. So I'm going to show you how to actually build this deep learning model for object detection. Then we're going to test it out. Ready to do it? Let's get to it. So, Nick, I tried your object detection course, but I got some errors. How many? A million. Well, look, how about we go on ahead and do it from scratch? No, wait, really? Yeah, well, the first thing that we need to do is get some data and label it. For this particular use case, we are going to be detecting our face using bounding box detection. This means that you'll be able to capture where your head is in the frame. Nice. What are some of the use cases for this? Well, you could use it for facial sentiment analysis or facial verification, but keep in mind that this is a generic object detection pipeline. So as long as you have one type of object, you could actually use this flow for just about anything. Cool, let's do it. Alrighty, welcome on back to the breakdown board. If I sound a little bit stressed, this is because this is the 6th time attempting to try to record this breakdown board. I'm gonna cross my fingers and hope all of this tech works. So, in this video, we are going to be very much doing an object detection model type tutorial, but we are going to be a little bit more practical and actually do a face detection model. So, the first thing that we are going to be doing is we are going to be collecting some images using our webcam. Now, from these images, what we're actually going to do is then begin annotating. So, we are going to take our images. Let's just imagine we have some luscious mountains in the background and the sun shining, and we have ourselves. Now, by annotation, what I actually mean is we're going to be drawing a bounding box. So we'll be drawing a bounding box around our head. So this will look a little bit like this. And in order to do that, we're actually going to be using a library called Label Me. So in the past, for object detection tutorials, I've used a library called Label Me, but actually not used Label Me. I've actually used a library called Label Image. But what I found is Label Me is really, really powerful because it allows you to do more than just bounding box annotation. If you wanted to do key point annotation, or if you wanted to do segmentation, you could actually use this particular library to do just that. Now, let's say, for example, we collect maybe 100-ish images. That's probably not going to be enough to actually train out a deep learning model. And this is where data augmentation comes in. For this, we're going to be using a library called Augmentation. I think that's how you pronounce it. Don't quote me on that. But what that is going to allow us to do is take our data set and apply random cropping, apply random changes to brightness, apply random flips, and apply random gamma shifts and RGB shifts. This is going to mean that we can take our base data set and flesh it out so that we have over 30 times the amount of data, which is going to take us, let's say, from 100 to 3,000 images, which should effectively be enough to actually build up our deep learning model. Now, this library is really, really powerful because it not only augments your images, it also does your annotations at the same time. If you imagine when you do a crop on your data set, let's say, for example, our full image was this, if I actually crop it out there, our bounding box coordinates actually need to change, right? So we actually need to shift those over. Augmentation actually does that for you. So it's super, super powerful and super, super useful. Now, once we've got our images and once we've got our annotations and once we've augmented them, then it's time to actually train our deep learning model. Now, if you think about what an object detection model is, it's really two different types of models. It's a classification model, which is trying to classify what the type of object is. Our particular case, it's just going to be one class, which is our face. And the second part is actually a regression model trying to estimate the coordinates of that particular bounding box. Now, we only really need two coordinates to draw a box. We need the top left or the top right, and we need the bottom left or the bottom right. So as long as we get two opposing sets of coordinates, we can actually use those to draw a bounding box. Now, before we actually go and train our deep learning model, we need to define the losses. So for our classification component, it's going to be a binary cross entropy loss, which is pretty common when it comes to actually doing a classification model. So this is going to be doing the face classification. So that's our loss for that. And then the second loss that we actually need is our localization loss. So what we're actually going to be doing is estimating how far off our predictions were from actually drawing that box. Now we are going to do it slightly differently. So we're going to take a look at our top coordinate and find out how far off our prediction was from that. And this is what this component of the loss is doing here. So you can see we're taking our x coordinate and comparing it to the predicted, and our y coordinate and comparing it to our predicted. So that's the first component. Then the second component of this loss is actually evaluating the width and height of that particular bounding box. So what we're going to do is we're going to compare our true value versus our predicted value. So we're going to compare that for our width, and then we're also going to do it for our height. And that is what these two parts of this loss are doing. So if you think about our localization loss, this is ensuring that our box is as close to possible or close to representing our object as possible. So once we've actually gone and defined those losses, we're actually going to use the Keras functional API to build up our model. Now we're actually going to be using a VGG16 model, which is a classification model for images. Now the beauty of this is that it's been pre-trained on a ton of data already. So we can actually just use it inside of our model and add in our final two layers, which are going to be our classification model and our regression model, to be able to give us our bounding boxes. So once we've gone and built up that model, what we'll get out of this model is 6 different values. So our first, 5 different values. So our first set of values is going to be either a 0 or 1. It's not going to be both of those. It's going to be a range within that value. And that's going to represent whether or not a face has been detected within our particular image. And then the second set of values is going to be a set of 4 values. And this is going to be x1, y1, x2, y2, which represents the coordinates for our box. So we'll actually get 5 outputs out of this model, which we can then use to be able to do detections. So once we've gone and trained that, we'll actually go and test it out in real time, and we'll make detections, which will effectively be able to go and detect our face. And that, in a nutshell, is the breakdown board over. Let's jump on over and get to coding.
Alrighty guys, so face detection. So in order to go through this, I've gone and written a ton of code which you're going to be able to leverage. And if you want to go through this code yourself, it is all available on my GitHub repo. So you just need to go to /face detection, and it is all there. Now, whilst I've called it face detection, what we're really dealing with here is an end-to-end object detection pipeline, because we're actually going to be doing bounding box detection, which you'll see in a second. So first things first, what is it that we need to go on ahead and do? Well, let's actually take a look at our pipeline. So first things first, we're going to deal with section 1, setting up and getting our data, as well as doing a little bit of annotation. So first things first, we need to go and install some dependencies. So if we open this up, we can see that we have 6 different dependencies that we need to go and install inside of our Python environment. Now, if you don't know how to work with Jupyter, or you don't know how to set up custom environments, by all means, go and check out the deep learning beginners tutorial. I show you how to get all of this set up. So effectively, you will be starting where I'm showing you right now. Cool. So first things first, we've got to go and install a bunch of stuff. So we need to run !pip, which is a standard Python installation. So pip install, we're going to be installing label me. Let me actually show you this. So label me. So this is quite possibly one of my favorite libraries that I've dealt with lately. So this allows you to do a ton of different types of annotation, and we'll probably be exploring this a ton more in the upcoming deep learning series, or wherever we're going with this stuff. So we're going to be using label me for our annotations, Tensorflow and Tensorflow GPU. So our friends are going to be helping us with deep learning. OpenCV-Python. So this is going to be used for real-time detection as well as capturing images, which you'll see over here. We're also going to be using matplotlib, and this is really to do our rendering. So right about here, we'll be using matplotlib. And then Augmentations. This is a new one. So this is what we're going to be using to do our data augmentation. So the nice thing about this is that if you go into the documentation, and again, I'll link to this in the description below. So if you actually go down, there's actually a walkthrough to do bounding box augmentation. Now, I mentioned it in the breakdown board. So a really important thing when you're doing data augmentation for deep learning and specifically for object detection is that you not only need to augment the images, if you start cropping the images, you need to augment the labels. And Augmentations actually does that for you. Absolutely fantastic. Cool. So let's go ahead and run this install. So we're going to be installing LabelMe, TensorFlow, OpenCV-Python, Matplotlib, and Augmentation. So if we scroll on down, doesn't look like we've got any errors there. So that is our first line of code successfully run. So we've now successfully gone and installed our dependencies and set those up. Now, the next thing that we need to do is actually go and collect some images. So in order to do this, we need to import 4 different libraries. So first up, we're going to be importing OS, and I've talked about this a lot before. So OS just makes it a lot easier to navigate through different file paths. So if you need to join file paths together, if you need to list stuff inside of directories, OS is your friend. So that line is import OS. The second line is import time. So when we actually go and collect our images, we want to give ourselves a little bit of time to move around. And that is exactly what this time library over here is going to help us do. We are then going to be importing UUID. So the nice thing, let me actually show you what UUID does. So UUID actually allows you to create a unique identifier, a uniform unique identifier. So if I type in UUID dot UUID1, this gives us a specific uniform identifier. So you can see that that is that identifier there. This allows us to create unique file names for our images. So rather than going image 1, image 2, image 3, blah, 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 so on, we're going to use this to make us look a little bit more professional. So this allows you to create uniform unique identifiers. So that's UUID. And then OpenCV, by now, if you're doing object detection, you probably heard about OpenCV a bunch. So OpenCV allows us to work with different sensors, different cameras, just makes our lives a whole bunch easier in order to do computer vision. So those are our 4 dependencies now imported. The next thing that we need to do is go and define some paths. So our images are going to go inside of a folder called data, and we're going to specifically put them inside of a additional folder called images. So we're going to specify this for now. So let's actually tweak this. So it's going to be os.path, and we're going to put it inside of data and inside of a folder called images. And the number of images that we're actually going to collect is, I've got 10 there, but we really need more than that. So we'll probably collect 100, to be honest. It's going to take a while to annotate these, but I want to show you a N10 pipeline. So let's actually collect 20 to begin with. And then what I might do is move the camera a little bit, collect another 20, move the camera a little bit more, collect another 20. I don't know, maybe change my shirt so that we've got different samples. So ideally, you want as much variability in these types of data sets that you're collecting. Let's collect 30 to begin with. And then we'll do 30, 30, 30. Okay, so our data is going to be os.path. This should be os.path.join. So our images are going to go into a folder called data and then images, and we're going to collect 30 images to begin with. Now, we first up actually need to create these folder structures. So if we go into our repositories, I'm working inside of Jupyter Lab. So a nice thing about this, just makes it a little bit easier to navigate through our file structures. So I'm going to create a folder in here, and I'm going to call it data. And then inside of data, I'm going to create another folder, and I'm going to call that images. And I'm going to create another folder, and I'm going to call it labels. So this is going to be where we store our raw data and our unpartitioned data. So in a couple of seconds, once we get into partitioning, or a little bit later on, once we get into partitioning, we're actually going to create 3 additional folders. So train, test, and val. And we'll actually split up our data manually. So there is a way to do it automatically, but to be honest, I was running out of time to get this tutorial done. This actually took me 5 days to write in total. If you have a better way to split it up, let me know. But for now, we'll just know that you need an images folder and a labels folder inside of a data folder. So this is my top repository. If I go into data, I've got a folder called images, blank right now. And inside of there, I've got a folder called labels, also blank right now. Now what we're going to do is we are going to collect a bunch of images. So Let's walk through this. So the first line is establishing a connection to our video camera. So again, if you've seen any of my computer vision videos before, this will be pretty familiar to you. So it's cap equals cv2.video capture, and then we need to pass through our camera number. So I think a lot of you have had problems with this before. When you are passing through this number, you might need a test, right? So the number for your particular webcam or your particular video capture device might differ, right? So the one that I'm recording this tutorial on right now is video capture device 0, I believe. And the one that we're going to be recording or capturing our images for, I think, is video capture device 1. But we're going to test this out and see if it works. Worst case scenario, if it doesn't work, you just rerun it, change the video capture device number, and keep testing until you get that right capture number. So that's our video capture device. Then we're going to be looping through our range of images. So we are going to be collecting 30 images. So we have written for image num in range, and then the number of images that we're going to be collecting. So effectively, we're just writing a loop. So for image num in range 30, print image num. Right, so we're just going through 30 different images. We're going to collect 30 to begin with, right? So it's just a basic loop. Then we're going to print out that we're collecting image, and we're going to print out which image number we're up to. We're going to read from our capture device. So again, this is common to a OpenCV image collection pipeline. So we're going to get a return value, so whether or not we've successfully gone and captured something, as well as the frame itself. So ret, comma, frame equals cap.read. So it's going to capture the frame, and it's going to allow us to write it down using cv2.imWrite. So this just defines the name of the file that we're actually going to be passing through, and we are passing through the images path, which is what we defined up here. So it should go data, images, and then a unique file name, which is based on UUID1, as I mentioned before. Then we're going to write it out using cv2.imWrite, and we're also going to show it back to the screen so we can see it. Now we're also using that time library that I mentioned up here. So we're going to sleep for, I believe it's half a second between each frame. So this gives us a little bit of time to move around, maybe move our head in around the frame, move it out of the screen, because we also want to capture a couple of frames with our face not in it. So this gives us some negative samples, particularly important for our classifier component of our deep learning model. And then all of this stuff down here is really just our usual CV2 break code. So it allows us to break out of the loop. Okay, so that is looking pretty good for now. So let's actually go on ahead and run this. Actually, I'm going to take down the green screen so that way we don't have we have a little bit of noise in our background rather than just a straight green screen. Makes it a little bit too easy for our deep learning model. All right, so that is the green screen now down. I mean, that actually looks pretty good in the recording over the green screen. All right, let's actually go and run this. So we should get a little pop-up towards the bottom of our screen, assuming everything is working okay. There we go. All right, so you can see that. So I'm just going to move around, smooth this out of the way. I'm also going to jump out of the screen completely. All right. So let's actually take a look inside of our images folder. So it looks like we've got a bunch of images. Beautiful. I don't like that we've got the mic in there, but that's fine. We've got a couple without, so you can see that we've got a couple with ourselves out of the frame as well. Looking good. Okay. So that's our first 30, but again, we probably want a lot more. So now in this set that we collect, we might move a little bit further back and collect another 30. So let's actually let me actually see. That green screen back. All right, let's actually collect another 30. And again, if you've already got images collected, you can just annotate those as well. Another key point to note. Let's collect another 30. I'm moving around. It hasn't even popped up yet. Okay, there we go. Boom. Move over to here. Over to here. Completely out of the frame. Move over to here. Go close. Let's actually do a couple where we're kind of close to the screen as well now. I covered my face a little bit. Alrighty, so that's 90 images now, or it should be 90 images. Let's actually go and take a look. How much data do we have? So if we go into images, let's see. We have 90 images. Okay, I think that's probably going to be enough to begin with. Let's see. Bring the green screen back. Okay. All right, so we've got images. So we've got this IPy checkpoints. I'm going to delete that out of there because we don't really need it. And then if we go into labels, we still don't have anything. So how are we doing so far? So we've got images. Where are we up to? So we have successfully gone and set up and got some data. We've installed our dependencies. We've now gone and collected 90 different images. And now what we're going to want to do is label those. So what we're going to do is we are going to annotate those images using a library called label me. So if I go and run !label me, this is going to trigger the label me annotation software or package, right? Now, again, you can run this from a command prompt. So if you open up a command prompt, you activate your environment and run label me at the command line, this will allow you to do it. But assuming you've got it installed from over here, you should be able to successfully use it. If you get stuck, go and take a look at the documentation because there is a bunch. So really, all you need to do is go to the command line, run pip install label me, and then go to the whatever command line you're using. Well, I'm using Windows over here. So it's really pip install label me, and then you run label me to start it, right? I'm doing it inside of a Jupyter Notebook because I want it to be inside of a Jupyter Notebook, but you sort of get the idea. So if we go and run this, we should get label me popping up towards the bottom here. And there you go. And what I'm going to do is we are going to open up the directory with our images. So we can actually over here, I don't know if I can zoom into this. So open over here, you can see it says open dir. So we can actually open that directory, go into our data folder, go into our images folder and select that folder. And look at that. We got our images that we just collected. So the other thing that we want to do is we want to change where our labels are going to be saved to, because what we're effectively doing is we're creating labels now, right? Pretty awesome, part of the deep learning process. So what we're going to do is hit file, and then we are going to hit change output directory, and I'm going to choose the labels folder. This isn't going to break anything. The only thing that's going to happen if you don't change the annotation folder or the output folder, it's going to save your annotation to a different folder. You just need to move them around. No biggie, right? So I'm going to choose that folder. Then the other thing that I'm going to do, and this is going to save us a bit of time, is if you go to file, save automatically, it's automatically going to save those annotations. So you don't need to hit save every single time. Just going to make your life a bit easier. Okay, so that is the beginnings of this. Look how nice that plant looks. That's a nice plant. I don't know what it is. Got it randomly. Okay, so those are our images. What we now need to do is annotate. So what we can do is just go over to here or over to edit, hit create rectangle, and then you're going to get this little crosshair symbol. To annotate, all you need to do is click the starting point for the bounding box and then click again. So if I click, you can see I've got a little green thing. And if I draw the box, look at that, and then click again, and it's going to ask me to name what type of class this is. And I'm just going to name it face. I don't know if you can see that, but you can see I've just written face because we're only going to have one class. And then we're going to hit OK, and that is our annotation. Then if I hit D on my keyboard, it's going to allow me to loop through each one of these. So again, I can draw another bounding box, face. This one's a bit blurry, but we'll do it nonetheless. Face. So again, all I'm doing is I'm clicking, drawing a bounding box, hitting OK. Clicking, drawing a bounding box around my head, OK. Clicking, drawing a bounding box, OK. And I'm just going to keep going. So for the images where we don't actually have a face in the frame, we're actually going to do nothing. So I've actually set up this code so that it will allow us to handle images where we don't have any examples. And even though the mic is in the frame there, we'll do it. I'm just going to keep doing it. So again, all I'm doing is I'm clicking to begin the annotation, drawing the annotation, clicking to end the annotation, and then hitting OK. And then I'm hitting D to go to the next image. Click, draw, click again, next. All right, so for this one, I'm going to draw, like it's going to be a bit sketchy, but I'm basically going to do that. So I've at least got part. All right, so for this one, our face isn't in the frame, so I'm actually going to skip that. So that means there'll be no annotation for that particular file, but that's fine. The code is actually set up to handle that. All right, so I've drawn, so bounding box there. bounding box there, bounding box there. This is a close-up, bounding box, bounding box. And the cool thing about this is that, like, once you've gone to the effort of, oh, hold on, no, this is not D. Delete that. Want face, boom. Face. How do we delete that annotation now that I've screwed that up? That's fine, we'll leave it. We'll review. Boom, face. Can we delete that? Edit polygons. So you can see that I've accidentally created a label list there with the D. I don't know if that's gonna, let's actually just quickly review our annotations. Actually, this is a good point to go and review. So we've gone and started annotating. What you'll actually see is if you go into the labels folder, because that's where we pointed our annotation. So if we go into data and then labels, you can see we've got all these JSON files. Now let's take a look at the last one, because just want to make sure. So this is what it looks like. It's looking okay. All right, so you can see that this is what an annotation looks like. So we've got the version, I believe, of label me, any flags. We've also got the shape. So this over here is what actually represents our annotation. So you can see that our label is saying face, and it's actually got the points. So these are the coordinates for our frame. So I believe it'll be, what will it be? So it should be the width first, and then the height, and then so this will be the first point at the top. This will be the second point at the bottom. Cool. All right, so these are our annotations. So that doesn't look like adding that, oh, hold on, this one's got D. So let's actually clean this one up. Let's take a look to see if it's screwed up any others. That one's okay. That one's okay. Which one was screwed up? So let's actually go back and find that one that we screwed up. So I'm just going to hit, there we go. All right, so you can see it there. I'm going to remove that annotation and save that. So that should hopefully fix it. So that was annotation for image 32FF80075. So these are things that happen, right? Like sometimes it'll screw up. You'll maybe write an incorrect annotation. I sort of wanted to show you this rather than make it all perfect and then you're like, Nick, it's not working. Okay, cool. So that looks like we've removed that. Let's just double check it's the same one. It's super small. No, that is not the same one. So 32FF805. It should be this one here. See, God, that is a long... All right, let's zoom out. Look at my head there. See if it's been... No, it's still in there. Why is it not deleting? All right, let's just go and do it manually. So I'm just going to step in to... I think it was this one, right? So I'm actually just going to delete it manually. So if we go inside of this, I'm going to delete all of that. Again, this is purely optional, but if you do screw it up, accidentally put an incorrect annotation, you can just delete it out of the shapes array. So you can see that there. I'm going to delete that, hit save. Right, so if we go and let's go back a little. Still looking good. Doesn't look like it's appearing anymore because we've gone and deleted it out. Okay, I think we're looking good. And again, so you can just go backwards and forwards, A and D. It's like the normal WASD. Okay, let's keep going. So again, we're going to draw another rectangle. And we're going to set it up as D. Keep doing this. No, we're going to set it up as face, not D. Really annoying me that I have to now go and delete. Let's actually save this. Let's close this and see if we can reopen it up and it's getting whether or not it gets rid of the D bit. All right, so let's open our directory. So data, images. And then if we go and open our labels, so we're going to change our output directory. So data, and then we can go into labels. All right, that looks like it's got rid of it. So you can see that we no longer have that D label appearing anywhere because we've gone and deleted it out anyway. Okay, so these are all of the ones that we've gone and successfully labeled. So just restarting label me, I think we'll pick up the new labels again. All right, so let's finish this off. So again, let's save automatically. We're going to go create rectangles. So let's do this. So we're going to finish it and hit face. All right, I'm probably going to fast forward through this so you'll see the end outcome. So let's probably speed this up. Key point to note, for the ones where my face is in there but my hands are covering it, I'm actually going to leave those in there and not label them. So I'm going to say the face is blocked so you can't actually see it. So for this one, I'm going to leave those. So no annotation. And again, I'm just trying to capture the majority of my head as well. Oh, almost did the D error again. Alrighty, those are all of our images labeled. So again, we've got some negative samples, got plenty of images and plenty of annotations. So again, we've done 90 images. And when we go and pump this through our augmentation pipeline, we're going to get a ton more. So I don't know, what should that mean? About 2,700 images. All right, so we've got a ton there or more. I can't remember how many we go and augment, but okay. So that is our set of annotations done. So what you should have is inside of our images folder, we've got a ton of images. And then inside of our, let's take a look. So image, we can open one of those up. So again, bunch of images. So we haven't actually gone and changed the image by annotating it. We're creating that annotation inside of a separate file. So those are our images, which are looking brilliant and beautiful. Then if we go into our labels, we've got our JSON labels. So again, the actual annotation is inside of this shapes key here. So shapes, 0, and then our points represent our coordinates. So what you can see there. Now we've only got one label, which is going to be face, but we've got all of these different points which represent the bounding box coordinates for our face. So we're going to be able to use those to do our object detection. So that is our first bit now done. So we've successfully gone and set up our implementation. We've gone and collected a bunch of images and we've gone and annotated using label me. Let's jump back on over to our client and have a chat and see what's next.
So we got data. Now what? Brace yourself. We got a fair bit of data pre-processing coming. We're now going to do a few things. First, we're going to take a look at some collected samples using matplotlib. Then we'll split it into a training, testing, and validation partition. Hold up. Why do we need to do that? This is best practice. The model is trained, aka taught, from the training partition. But at the same time, we use the validation partition to inform how we build the neural network. So if we see the model is performing well on the training partition, but it's shaky as hell on the validation set, it might mean that we need to try some regularization or change our neural network architecture. What about the test set? We'll leave that bit right up until the end to finally see how our model has performed. This should be a clear test of performance because we haven't used it in either our training or to determine how the model is built. Ah, got it. What else are we doing here? A major key. Yeah, alright, DJ Khaled. Some may say I am the DJ Khaled of deep learning. Seriously. Nah, we're going to apply image augmentation to build out our dataset. We'll randomly crop and adjust our images to go from a small set of data to something way larger. In this case, 30 times bigger. Ah, sweet. Let's do it then.
Alrighty, and we're back. So our client's pretty happy. We've gone and collected a bunch of images of our face and we've gone and annotated them with label me, as I showed you down there. Step 2. So we've got a bunch of stuff to do with this. So we're going to be going all the way up to step 7. So first up, we're going to review our data set and build an image loading function. We are then going to partition our unaugmented data. So we're going to be splitting out the images and the labels that we just collected. We're then going to apply our image augmentation on our images and our labels using augmentations. We're then going to build and run that augmentation pipeline, and then we're going to prepare our labels and combine them all. So by the end of this particular part, we should effectively have a data pipeline. So we'll have a training, testing, and validation data partition with our augmented data, which has been gone and reshaped and pre-processed. And we should be ready to pass this through to our deep learning model once we've gone and done all of this. Okay, so first things first, let's go on ahead and kick this off by reviewing our data set and building our image loading function. So first things first, we're going to import a number of key dependencies. So we're going to be importing TensorFlow. And in order to do that, we're going to run import TensorFlow as TF. So what you can see there, and TensorFlow is going to be used to build our data pipeline as well as to, what are we going to use it for? To actually build our deep learning model a little bit later on. Now we need to import it a little bit earlier on, at least at this moment, because we need to limit the GPU memory growth. By default, TensorFlow is going to expand and use all of your VRAM. So we need to implement memory growth limitation right up here. So you need to do it pretty early. We're importing CV2 again, but I think we've already got it. So we don't actually need it there. I can actually take that out. So the next thing that we're going to import is JSON. So import JSON. Now, why do we need JSON? Well, if you take a look, our labels are actually in a JSON format. So you can see that there. So we're going to need the JSON library to be able to load those into our Python pipeline. Then we're going to import NumPy. So NumPy is going to be used to just help us with our data pre-processing. So we've written import NumPy as NP. Then we've imported matplotlib. So from matplotlib, import pyplot as PLT. And we're going to be using that down here to actually visualize our images. So let's run those. So TensorFlow does take a little bit of time to import every now and then. Keep in mind as well, if you've got a GPU, this is going to train way faster. So if you want to learn how to go and set up TensorFlow for your GPU, again, jump back on over to the Deep Learning for Beginners tutorial and I'll actually walk you through it. All right, so those are our 4 dependencies now imported. So again, we imported TensorFlow, JSON, NumPy, and matplotlib. The next thing that we need to do, so step 2.2, is limit our GPU memory growth. So again, this is some pretty stock standard code that you would have seen me use a ton of times. Really, first up, what we're doing is we're grabbing all of our GPUs and then we're setting our memory growth equal to true down here. So I won't explain that too much because we've gone through it a bunch of times. Just know that it's good practice to implement this when you're using TensorFlow because it's going to ensure that you don't get too many out of memory errors. Yeah, got that in there. That's pretty self-explanatory. And then we also want to test whether or not our GPU is available. So we can write tf.test.isGPU available. It normally says this is going to be deprecated, but I still use it even though it is. So it has returned true. So you can also run this command here instead of this one. So let me actually show that. If I went and grab that, this is the proper way to actually go and do it. So you can see that our GPU is showing up there, which means our GPU is available for deep learning. Okay, cool. So that is step 2.1 now done and 2.2 done. So we've gone and imported TensorFlow, we've gone and limited our GPU memory growth. Next thing we need to do is load our images into our TensorFlow data pipeline. So in order to do this, we are going to write images equals tf.data.dataset.list_files. Now I can already see an error in this, so we're going to need to tweak this. So what we need to do is we need to pass through the full path to where our images are. And we also need to include a wildcard search, which is this bit here. So let me explain. So right now we've got our data inside of a folder called, so if this is where our Jupyter notebook is, so you can see face detection.ipynb right there. Our data or our images are currently inside of data, inside of images, and then over here. Now, I think I was playing around with this to test out training data, but that's fine. So because our data is inside of data and inside of images, we can actually get rid of this train bit. But once we set up our training folders, we might want to tweak this. So we're going to put through the full file path to where our images currently are. So in this particular case, they're inside of data and inside of images. I'll probably go and update this in the code afterwards. So it's inside of GitHub, or at least you've got the full base flow. So it's currently inside of data and inside of images. So data, images. So it's right here, which means that we are going to look inside of the data folder, look inside of the images folder, and then this is the wildcard search. We're going to look for anything which has a .jpg extension. So you can see we are looking for a star and then .jpg. So anything with .jpg, we're going to pick this up in terms of its file path inside of the TensorFlow data pipeline. So I'll show you what this looks like in a second. And then we're going to set shuffle equal to false because we don't want to shuffle. I didn't realize shuffle was a thing included. And this was causing me a ton of headaches previously as I was building this up. But just know we're not going to shuffle it for now. If I actually go and run this, then what we should be able to do, let's take a look at what else we got here. Let me show you this first bit. So if I type in images.asNumPy_iterator.next, it's going to return the full file path to an image. Now, really important thing to note is if you go and run that line and you've got nothing in there or it's not showing any images paths, that means it has not picked up your images, which means the rest of this isn't going to work. So make sure you've got this full file path set correctly because it is really important to ensure your images are getting picked up. In this particular case, this is what you should be getting. Again, the file name is going to be different because the unique identifiers are going to be different every time, but you should at least be getting a file path out of this. Now, you're probably thinking, well, Nick, this hasn't actually gone and loaded up an image. What the hell? We actually need an image to do object detection. So that's exactly what this next step is going to do. So we're actually written a load image function. So we can actually, I'll leave that there for you. So we can write def, or we've written def to define a new function, and the function is called load_image. To that, we are going to pass through the full file path. So this is what we're going to do down here when we use this actual function. So we'll pass through the file path, which is effectively going to be this. And this is going to use 2 lines of TensorFlow code to actually read in our image. So first up, we're going to run tf.io.read file, and that is going to take in the file path, which is going to return a byte encoded image. Then we can run tf.io.decode JPEG and then pass through that byte image. So this goes into here, and then we get our image back. Then in terms of using this with a TensorFlow data pipeline, you can actually use the map function. So if we go TensorFlow data, there it is. I've opened this up so many times. So the documentation for this is right over here. So on the side, it should say map over here. So this actually explains what happens. So this map applies map function to each element in the data set. Now the map function in our particular case is called load image. So it's going to apply that load image function on each value in our data set, which in this particular case are these file paths. So it's going to go through and actually return our image. So if we now go and run this, we actually need to run the load image function. We go and run that. Now we're going to get our image back. So we're effectively now mapping through each one of those images, and we're now actually able to get an image back. So this is what you should look, or what it should look like after you've gone and run through that data transformation. Now what we can actually go on ahead and do is visualize those images, because we've now gone and picked up all of our images from our images folder. We can actually go and visualize them. So that is step 2.1, 2.2, and 2.3 done. So we've successfully got some images inside of our TensorFlow data pipeline. And what I mean by TensorFlow data pipeline, if I type in type and then images, we've actually gone, yeah, that's fine, type and then images. You can see that this is actually a TensorFlow data pipeline. So the fact that it says TensorFlow Python dataset ops, that is a TensorFlow data pipeline. And again, because the last function or transformation that we chained onto it was that mapping, you can see it's returning map dataset. Cool, so that is looking okay. Now we can also go and visualize these images inside of matplotlib. So we can go and batch these images up. So again, this is another function available inside of the TensorFlow dataset API. So let me show you this one. So if I go and select batch up here, you could see this component basically batches our images up. So rather than returning one image, it's going to return the number of values inside of a batch. Pretty common when we go and do deep learning. So here we are going to batch it up into a set of 4 so we can visualize 4 at a time. So image_generator equals images.batch, and we're going to put 4 in each batch, and we're going to return .asNumPy iterator. So this actually allows us to loop through our images and get them back. So images_generator, we can then run images_generator.next to get a next batch. So plot_images equals image_generator.next, and we can actually run this line multiple times, and it's going to return a new batch of data each and every time. That's what the TensorFlow data pipe or TensorFlow fit model actually does, or fit function actually does. It'll go and run next, train on a batch. Run next, train on a batch. Run next, train on the batch. You get the idea. So if I go and run this, and then we go and run the next line, this is just going to loop through and visualize our images. So it's just using matplotlib and the subplots class here to actually do this. So if I go and run that, you can see we've got 4 images. Pretty cool. We can go and run next again. We're going to get another 4 images. Run next again, another 4 images. Next. How cool is that? So we can now see a bunch of images that we've got. Now you can see that right now they're not shuffled. So because it looks like it's actually like a moving image. Pretty cool, right? Now, if we wanted to, we could actually enable shuffle up here and we'd actually get random images. So let me show you that. So if I disable shuffle here and we go and visualize, so you can see they're all going to be slightly more random now, right? So you can see that it doesn't look like it's a sequential set of images. It's definitely a lot more random. Cool. All right. So we now have our images now done. So that is part 2 now done. So we've now gone and reviewed our data set and built at least our image loading function, which we'll be able to use later to build up our TensorFlow data pipeline. So we imported TensorFlow, limited our memory growth, and took a look at how we can load images into our TensorFlow data pipeline. We also went and visualized our images using matplotlib. Next thing that we need to do is partition our unaugmented data. Now this is manual. So I've written here, this step is manually splitting our data. And I've done this because it just gives you a little bit more control over actually splitting this. If you wanted to use scikit-learn train test split to actually do this, by all means, go ahead. Again, I was running out of energy by this time to go and do that. Full disclosure, I wanted to be real with you guys. I always try to be. Again, it's not all that Pythonic and it's probably got some duplicate code, but it does work. It does work, okay? So that's a key thing to know. So what we're going to do now is we're going to go and move our data into train, test, and validation partition. So we need to create a couple more folders. So inside of our root folder, actually inside of our data folder, we're going to create another couple of folders. So we're going to create a train folder, we're going to create a test folder, and we're going to create a val folder. So we've now got 4 folders there. So train, test, and val. Inside a train, we're going to create another folder called images, another folder called labels, and then we're going to jump back. So inside a train, we've now got labels and images. Then inside of tests, again, we're going to do the same, labels, images. So again, inside of tests, we've now got a labels and images folder, and then inside of val, we're going to do exactly the same. So labels, images. Okay, so it should now look like this. So our data folder has now got a folder called labels, called the images, and these are the raw ones that we've gone and collected, or the unpartitioned data. And then we've got a folder called train. We've got, again, a folder called labels with nothing in it at the moment. And we've also got so labels has got nothing in it, or images got nothing in it, labels got nothing in it. Test, again, labels, nothing in it, images, nothing in it. And then if we go into val, same thing. All right, you get the idea. So that is our set of folders now set up. Now, what we actually want to go on ahead and do is actually move some data in there. So I'm just going to jump into the folders. And I'm just going to go and set a bunch of images. So let's actually work out. So we've got 90 images total. So let's say we want, 70% assigned to our training data. So let's say 0.7. So we'll assign, let's say 63. So we're going to assign 63 to train. And then let's go and assign, let's say 15% to both val and test. So 90 multiplied by 0.15. And then we'll assign, what is that? So we'll be doing 14 and 13 maybe. So 14 and 13 to, test and val. So that means, 63 plus, 27 down here, we should have the full 90. Wait, is my math right? 63 plus 27. Yeah, my math's right. So 90, cool. Sorry, mind blank there. Okay, cool. So we've now successfully got our images now allocated. What we actually need to do is actually go and split them up. So let's go and grab, what are we getting? 63 for train. So we're just going to randomly select, and again, this is not all that scientific, but I'm just going to grab 63 images, which is going to be the large majority, right? This is my random split function, me just randomly clicking. I'm just monitoring down the bottom to see once we get to 63. There's not too many. We probably should have got some more data. We could always add more later on. But keep in mind, we're going to augment as well, right? So we are going to be able to have a whole bunch more data. So that's, yeah, okay. Boom, boom. All right, that's 63. So I'm going to cut those and I'm going to put them inside of the train folder. So I'm going to cut, go to my train folder and go into the images folder inside of train, paste all of those there. So that is 63 images inside of the train images folder. Now we're going to go into images again, and we are going to get 14 for, what is it, for val or test, whatever, one of those. What's happened there? Why do we... 39, okay. Wait, why is that 39? Looks like we copied and pasted them there. So what do we need? We need 14. Right, that's 14 images. So I'm going to go and throw those into... Let's put that inside of test. So 14 into test. All right, so we've got a bunch of variations. So again, some of us without a class or some of those without a face in it. So let's go back into the, let's grab the rest. That's train. So we want to go back into the raw images folder, grab these last ones, and we're going to throw those into the val folder. Wait, we've already got them. No, yeah, val. Cool. All right, so we've got 13 images inside of val. We have how many inside of train? We've got 63 inside of train. And if we go into test, we've got 14 inside of test. Cool. All right. That is looking good. So 63 assigned to train, 14 assigned to val. I think, no, we assigned, God, I can't remember now. We assigned the rest to val and test, but let's just make sure we've got this noted. Where are we? We are inside of, let's go check test. So how many is inside of test? So we've got 14 assigned to test. Okay. 14 to test and 13 to val. Okay. So those are now successfully assigned. Now, rather than doing the exact same for the labels, I've gone and written a script which basically loops through the train, test, and val folder. And again, it's looking for those folder names. So you got to ensure that they're the same. So train, test, and val. So over here, we have inside of data. So we've got train, test, and val. And inside of those, we've got labels and images. So what it's going to do is it's actually going to move the associated labels from the raw folder, which is inside of, currently still inside of the root labels folder. It's going to grab all of these and it's going to move them into their respective matching folder. So it will match them up to val, train, and test. So if I now go and run this, all things holding equal, we should effectively have our labels moved over. So if we go into labels, you can see there's nothing left there. Now, if I go into train and labels, you can see it's going to move those annotations. So if we go into test and labels, going to move those labels as well. If we go into val and labels, you can see it's going to move all those labels. So that is our data now partitioned. So we've now successfully gone and partitioned out our unaugmented data. So again, remember what you need to do is you need to go and move out of the data out of the labels and images folders into those val, train, and test folders. Now, if you go and add more data later, effectively all you're going to need to do is go and push that data back into those folders again and push the annotations into their matching folders so that when we go and do augmentation, it does the exact same. Okay, so that is step 3 now done. So we've successfully gone and moved over our unaugmented data and we've gone and moved over the labels. Now we are up to applying our image augmentation. So first thing that we need to do is import Augmentations. So again, Augmentations is this library over here. And if you actually scroll on down, it shows you how to actually use this. So we effectively set up a transformation pipeline, which looks like you can basically assign a whole bunch of different transformations. So over there, you've got random crop, horizontal flip, random brightness, so on and so forth. There's a whole bunch of others. I think we're going to use some others as well. And then you need to pass through your bounding box parameters as well. Okay, so first thing we need to do is we need to import it. So I'm importing Augmentations as ALB. So give that a sec. Water break. Running out of, my throat is going. Okay, so then the next thing that we're going to do is actually define our augmentation pipeline. So this is what the recommended, not the recommended one, what the example one looks like. I've gone and added a bunch of other things. So let me actually break this down so you can see it. Boom, and then, yeah, boom. Okay, so what we've actually got is 6 different augmentations that we're going to apply. So we've got random crop, horizontal flip, random brightness contrast, random gamma, RGB shift, and vertical flip. So these ones are actually going to, the random crop is the trickiest one to handle if you were to do this. Or actually, no, random crop, horizontal flip, and vertical flip are tricky to handle if you didn't have something that does your annotation augmentation as well. Mind blank. Okay, so alb.randomCrop, we're specifying how big our augmented images are going to be. So we're actually going to cut them down to 450 by 450 pixels, because right now they should be, what is it? So if we take a look at height, so it should be 480 pixels by 480 by 640. So it's going to be basically 480 by 640. So we're going to cut them down a little bit. So that means that we can do that dynamic crop. Then we are going to, and let me actually just show you that. So if we go and grab an image, cv2.imread, let's grab an image. So if we go into train images, this is purely optional. I'm just showing you guys os.path.join, train. So it should be inside of data.train.images, and then let's grab one. Right, so I'm just grabbing a random image at the moment just to take a look. So let's actually assign it a variable name. So image.shape. Yeah, so 480 pixels high by 640 pixels wide by 3 channels deep. So again, we're going to be cropping that down. And this might vary. So if you capture images of different sizes, or if you've captured images on your iPhone, again, you can still use this. Just be mindful of the image shape. So you at least want it to be, or the minimum dimension needs to be, should ideally be bigger than whatever you're going to crop it to. So if your image is 100 pixels by 100 pixels, well, you're going to have a hard time cropping it to 450 by 450 because it doesn't even meet those minimums. So just something to keep in mind there. Okay, so that is our augmentation pipeline. So you can see inside of square brackets, I've got those different transformations there. This is my OCD kicking in. It kills me that wasn't aligned. Okay, so we've got random crop, horizontal flip, random brightness, random gamma, RGB shift, and vertical flip. You could take some of these out. You could add more in if you wanted to. I've just found that those 6 give us a sufficient amount of data. And then we are going to specify our bounding box parameters. So in this particular case, we're specifying the format of our annotation. So let me actually show you this because it's really important. So if you get annotations different formats, it's important to note that you need to go and change the format down here. So right down here, this is the different formats that it's expecting. So Pascal VOC is a really popular format. So you've got Xmin, Ymin, Xmax, Ymax, and these are unnormalized images. So they're not all unscaled images. So this hasn't been adjusted for the size of the image. So you can see it's got the raw image size. So 98, 345, 420, 462. We are going to go and divide our images by the shape of divide our labels by the shape of our image. So you can see there that these ones have actually been normalized. So they've been scaled for the size of the actual image. So rather than having the raw coordinates, they've actually been divided by the width, by the height, by the width, by the height, which is exactly what we'll do. You can also use Coco or YOLO as well. So those are, again, each one of those different models has a slightly different way of representing the annotation. So we actually start off in Pascal VOC and then we go and adjust it to be inside of this Augmentations format as well. Okay, so that is our augmented done. So I've just gone and run that. So that is our augmentation pipeline now set up. Now what we can go on ahead and do is go and test this out. So the next thing that we're going to do is actually load up an image and run it through the augmentation pipeline. So first thing what we want to do is load up an image using cv2.imread. And to that, we're going to pass through an image from our training data set. So data, train images, and then you need to go and replace whatever this file name is here. If you go and run this right now, let's run this. Oh, that image exists? Weird. Okay, so maybe it's gone and generated that. Actually, no. So if I go and run image, you can see it's blank. So if I'm running that, it's blank right now. So it won't throw an error. It'll just return nothing. And that is because this image doesn't exist right now, which is what I was expecting. So if we go and grab this image though, so grab that image name and paste that. Is my head covering that? Yes, it is. And go and paste that in there. Now, if I go and run this, you can see our image is returned back. So just something to keep in mind. So it won't throw an error. It just won't return an image. And you'll be sitting there like, what is happening? It's not working, Nick. Just keep in mind that you need to go and pass through an image or the image name from your actual images folder. Okay. Then what we can go on ahead and do is load in our matching annotation. So we're going to go into our os.path.join. We're going to go into our training folder and into our labels folder, and we're going to grab the matching annotation. Now, assuming we actually have a face inside of this image here, the annotation name will be the exact same as the image name, except the only thing is the extension will be JSON. So if I go and paste that there and run this, looks like no issues. So we can actually take a look at our label. Boom, look at that. So we've got our label. Cool thing to note is if you wanted to go and grab the class, so we can go into, again, this is a dictionary. So let me show you. So type. It's a dictionary, so we can just navigate it as a dictionary. So we can go into shapes. And that gives us our annotation. Go into, you can see that that is inside of a list. Right? To go into a list, we can use number indexing. So we can go grab index 0. And then we can go and grab our class. So if we wanted to, we've only got one class. Again, let me know in the comments below if you wanted me to do more for multi-class or multi-object. So that's our label. Then we can go and grab our points as well. So if we go and grab points, boom, those are our points. Pretty cool, right? Okay, so that is our image successfully loaded, our coordinates successfully loaded, or our annotations. Now what we can go on ahead and do is extract coordinates. So we are going to do exactly what I've shown you up here. We're just going to store them inside of a coordinate array that you can see there. So if I go and run this and go and take a look at coords, and again, this isn't super Pythonic, but again, just for ease of reading, I'm showing you what it looks like. So we've now gone and taken what you can see over here and transformed it into a simple vector, right? So it's not a it's not a, what is it? A tensor, which is higher than rank 1. So we've effectively just got a vector over here with all of our coordinates. So 191, 191, 77, 77, 350, 350, 315, 315. Quick drink break. All right, so this is going to be x1, y1, x2, y2. So this will be the top coordinate. This will be the bottom coordinate. Now, the next thing that we want to do is go and do that transformation that I was telling you about. So is it going to be x2? Yes, because x, yeah, okay, cool. That makes sense. All right, so we're going to go and convert this set of coordinates into, so you saw that we had Pascal VOC here, which is unadjusted for the size of the image. So this is based on this raw image over here. So it's 98,345, which should be 98,345. And then let me zoom in because you probably can't see that. You can see that this annotation is 98 by 345, 98 by 345, which is that, and then 420 by 462, so 420 by 462. What you effectively go and do is you go and divide this particular value by the width of the image, so it'll be divided by 640, this particular value by the height of the image, so it'll be 480, so that gives you these sets of values over here, right? That's effectively what we're going and doing over here. So we're grabbing our raw coordinates, which is this, and we're dividing it by the width of the image and by the height of the image. That will divide these two. And then we're going to divide this value by the width of the image by the height of the image. That will divide these two. So we're going to run this and take a look at our coords. Boom. So we've now gone and transformed our coordinates from the raw Pascal VOC format, which is this over here, to the Augmentations format, which is this over here. Okay, cool. So that is looking good. Now what we can do is we can actually go and run that image and those sets of coordinates through our augmenter. So what we're going to actually do is return back our augmented, what is it? I think it actually returns back a dictionary. So augmented equals augmenter. And then to that, we're going to pass through our image. We're going to pass through our bounding box coordinates, and we're going to pass through our class label. So if I go and run this, let me show you augmented. So you can see you actually get a dictionary back. So let me prove that to you. So if I type in type, got a dictionary, and that dictionary should have 2 keys. So it's got 3 keys. So it's got an image, it's got bounding boxes, and it's got class labels. So if we go and take a look, so images or image, right? So that's our image, which should now be 450 by 450. Because remember, this cropping is going to change the shape of that. Then if we go and take a look at our labels, is it label or labels? Can't remember now. Labels. What is it? B boxes, not labels. B boxes. right? So those are our coordinates, and you can see that they differ from our raw coordinates. That's because we've gone and probably done a crop. So if we go and take a look now, so these two lines are actually going to allow you to visualize that. So cv2.rectangle actually draws a rectangle on an image. So whenever you see the cool object detection tutorials, that's probably what's being used. So augmented, so to that we are going to pass through our augmented image, so this. And then we're also going to extrapolate and get the two tuples that you need to actually draw the bounding box. So just know this is the topmost coordinate, this is the bottommost coordinate. So over here, what I'm doing is I'm just grabbing the first two values. So let me show you. These are the first two values. So if we go and take a look at augmented boxes, B boxes, you can see first two values, so 53.33. And remember, these correspond to X min, Y min. And then if we go and grab the last two values, which should be like this, last two values, this is going to represent X max, Y max, which is this value and this value over here. So now, and then the other parameters. So you also need to represent this as a tuple, and we're going and rescaling it to represent the size of the image. Because once you go and transform it into normalized values, you need to go and untransform it in order to go and render it. Otherwise, it's going to look really, really small. So that's that transformation that we're doing there. We're also representing it as an integer, and then we're passing it through as a tuple because that's what OpenCV expects. And then we're also dynamically changing, or we're not dynamically changing the color there. We're just specifying what the color is. And this should be in BGR format. So blue, green, red, and then the thickness of the actual image or the actual rectangle. So if we go and run this, look at that. So it's actually gone and flipped our image, and it's also gone and drawn the bounding box around it. Now, even though it's showing up blue, it's not actually blue in reality. It's showing up blue there because OpenCV reads an image as BGR, but Matplotlib renders it as RGB. So that's fine. It's not actually blue. Just keep that in mind. But you can see that it's successfully gone and augmented our bounding box, but it's still showing up around our face. Now, we've only done this for one image, right? So I've sort of shown you and walked you through it for one image, but I really wanted to drill into this because I think it's such a really, really important topic. So that is for step 4 now done. So we've set up our augmentations and our pipelines. So we're actually going to use this for our full-blown pipeline now. We've gone and loaded a test image and tested it out. We've gone and taken a look at what the annotations look like, gone and applied some augmentations, and then we've also gone and visualized it. So that is step 4 now done. We are now up to step 5. So the first part of work that we're going to do inside of step 5 is run our augmentation pipeline over our training, testing, and validation partitions for all of our images. Because up until now, we've only really done it for one image, right? But we need to do it for all of our data to get true value. Now, this is a ton of code and something that I spent a while writing up. So probably not worthwhile going through every single line in great detail, but I'm going to explain to you at a high level what is actually happening here. So first up, what we're going to do is we're going to loop through our training, testing, and validation folders, and we're going to grab every single image inside of that. We are then going to double check whether or not an annotation exists for that image. Because remember, some images aren't going to have our head in them. If an annotation doesn't exist, well, we're going to create a default annotation, which is this set of coordinates here. So we're just basically going to assign a 0 set of coordinates. And at the same time, we're also going to assign a class of 0 down there. Now, assuming a set of coordinates do exist, we're effectively going to go and do that exact same transformation over here, which is what we did right up here. So we're extracting our coordinates and we're taking it from a set of, or a tensor, which is a stacked array, to a straight vector, which is what you can see down there. So that is exactly what these two lines of code are doing. So up until now, from these, all we're doing is loading up the image and we're loading up the labels. Then what we're doing is we're going and creating 60 images per base image. So for X in range 60, so this means that we're going to be creating 60 augmented images for every single base image. So that means that for our 90 images that we created, we're going to be creating 90 multiplied by 60 images or raw augmented images that we're going to be able to use. Then effectively what we're doing is we're running our data through our augmentation pipeline, which is what you can see there. So augmented equals augmenter, and we're going to effectively be doing what we did just here. So we're just going to be doing it for 60 times to create 60 different images. Then what we do is we write out the augmented images, or the augmented image, and we're going to be putting that inside of a folder called AUGData. So I'm actually going to show you how to set that up in a second. And we're going to do likewise, we're going to transform our coordinates and we're going to write down those annotations using json.dump as well. So by the end of this, we should have 60 multiplied by 90 images and annotations for our training partition. Likewise, the exact same for 60 by 90 for all of our data, right? But remember, we've partitioned it out. So we're going to have some of those split up into training, testing, and val. Okay, so this is going to do a ton of data augmentation for us. If you wanted to do more data, you could actually just bump up that number there. So let's say you wanted 120 images per base image, it'll be 120 here. I found that 60 is a good mix and gives you enough data. So let's zoom back in. Cool. All right, so we're there. So what we now need to do is set up where our augmented data is going to be. All we need to do is go back into our root folder. So this is our raw data here, right? So we're going to create a new folder called org_data. And inside of that, we're going to create a training. So train, test, and val folder. And we're effectively just going to replicate what we did for our data folder. So inside of val, we're going to create a folder called images, and then a folder called labels. And then inside of train, we're going to create a folder called images and labels. And then inside of test, you guessed it, we're going to create a folder called images and labels. Boom. Right, so we've now got 3 folders inside of org data. So we've got a val folder, which has labels and images. We've got a train folder, which has labels and images. We've got a test folder, which has labels and images. But as of right now, we don't actually have any data in there. We actually need to go and run this augmentation pipeline to do that. So let's actually go and run this. So if we go and step out of it a little bit, now this will take a little while to run because it's doing quite a fair bit of stuff. But if we actually go and run this, you can see we've got the little star over there. So this is now running our, oh, that search has popped up. It's happening over here. So you can see that we are now running our augmentation pipeline. So let's give that a second to run and then we'll be able to test it out and see how it all looks. Cool. So that is now done. So you can see that our code cell is successfully completed. Doesn't look like we've got any errors there. So there's this over here. So I've actually set it up so that if we've got invalid annotations for whatever reason, it's actually going to drop them as well. So just keep it looks like we've dropped out 2 images there. Perfectly fine. You're still going to have a ton of data, which is why I set this to 60 up here. Okay, let's zoom back in. So now if we go into our org data, if we go into train and images, let's open that up. Yep. All right. We got a ton of images, right? Now, if we go into our training folder and if we go into labels, we should have a ton of JSON labels. There you go. So this is what our augmented labels look like. So we've got our bounding box, which represents all of our 4 coordinates. We've got our image and we've got our class. So we now have a ton of augmented data. And again, you can see that our images are now 450 by 450 as well. So this is how to look at it manually. Let's just double check test. So we've got labels in there. And we've got images. And if we go into val, should have labels. Perfect. And we've got images as well. All looking good. Alrighty, cool. So that is looking good for now. You can save this. So next thing we want to do is actually load some augmented images and take a look at them inside of TensorFlow. So this is where it gets unpythonic. I wasn't too happy with what this code looks like, but it works, okay? So if you've got a better method of actually going and building these up, again, you could just loop through and build this. But in the interest of getting this tutorial out in time and showing you how to actually do this, I actually went and just copied the code 3 times and relabeled the variables, but it does work. Okay. So we're now going to load in our images into our TensorFlow dataset. So our training images are going to be inside of a variable called train images. Our test images are going to be inside of a folder called test images, and our validation images are going to be inside of a folder called val images. All we're doing is exactly the same as what we did right up at the start. We're using the tf.data.dataset.list files method, and we're grabbing or using that wildcard search to pick up data out of our train folder inside of our augmented data repository. We're then using the load image, and we're using map to actually load that image up. We're then resizing our image to be 120 pixels by 120 pixels. So we're compressing it even more. And the reason that we're doing this is that we are able to make a more efficient neural network that way. So that means there's less data that we need to pass through to the neural net. Still seems to work fine. And we're also scaling our image. So we're dividing it by 255. So rather than our values being between 0 and 255, they're now going to be between 0 and 1, which means that we can apply a sigmoid activation to the final layer of our neural network. Okay, and keep in mind we've set shuffle equal to false here. So really, really important because we're going to go and load our labels in the same format. So we need them to be in the same structure. Okay, so that is our, those are our image pipelines now set up. So if we go and run this runs pretty quickly. So if we go and take a look at train images as numpy iterator next. So that is our image. And you can see that it's now much smaller values. This is because we've gone and scaled it over here. Cool, right? Okay, next thing what we want to do is we actually want to go ahead and prepare our labels. So again, we are just going to write up a function to load our labels. So def load underscore labels, and we're going to be using this similar to what we did for our images with the map function inside of the TensorFlow dataset API. So def load underscore labels, we're going to specify the label path, and we're really just going to use a with open statement here. So with open, and we're going to grab the actual label. To grab that, we need to use the .numpy function. We're going to read it in and return the label over here. And we're going to extract the class and the bounding box. So what we're actually going to be extracting is if I go into labels, we're going to be extracting the class, which is this, and the bounding box, which is this. So in this particular case, that there mustn't been a face in that particular image that it's gone and annotated, hence why these are all 0. Let's find another one. It looks like it's all 0. Stop. All right, so this one has got an actual annotation. So you can see we've got our coordinates and we've got our class. What this is doing down here is it's just going to return an array, or actually going to return 2 arrays, one of which returns the class, so 0 or 1, and the second actually returns the bounding box. But again, I'm going to show you that in more detail in a second. Okay, so that is our label loading function. So we can go and run that particular cell there. And then we're going to load the labels to our TensorFlow dataset. So this is also key point to note, that's step 5 now done. We're now up to step 6, which is what we're doing right now. All right, so step 6.2. We're going to use tf.data.dataset.list files, so pretty similar to what we did for our images, but this time we're going to be loading our JSON objects. And over here, we're just doing it for our train functions at the moment, and then we are going to use the .map function. This is weird. So I had to do some screwing around to get the label loading to work with the TensorFlow dataset pipeline because it doesn't by default render the actual label, but just know that I've wrapped it inside of this tf.py function here to have these strings available to our loading function, but it does work. So train underscore labels.map, we're passing through using a lambda function. So that means it's going to loop through each individual file name. We're then wrapping it inside a tf.py underscore function. And we're using this load labels method over here. To that, we're going to be passing through our labels, our file paths, which is what we're getting. Let me actually show you this. Let's run this first. We're trying to explain too much. So train underscore labels dot as numpy iterator dot next. All right, so you can see we're getting the full file path to that particular JSON object. This is going to be passed through to this. So ignore all the complexity that you're seeing here. Just know that this particular file path is being passed through to this with open statement, and we're going to be returning our annotations back. Okay, so that is that now done. So let's go and run this. And then we are going to do it for our test labels, and we're going to do it for our val labels. Again, non-Pythonic and duplication of code, I know, but it definitely does work. Okay, so those are our labels. Let's actually take a look at those. So if I go to train labels, train underscore labels dot as numpy iterator dot next, you can see that we have 2 values being returned. So we've got this array, or this first array, which is the class, so face or not face. And then we've got this second value over here, which is our set of coordinates. So we are looking, I was just noticing there's a ton of sun coming in this way now, but that's fine. Okay, so those are our labels and our images now loaded. So we've gone through and run our load labels function over each value or each JSON object or file path inside of that data set. And we've gone and loaded it using that load labels function. The next thing that we need to do is just combine our label and our image samples. So think about when you go and train something like scikit-learn or inside of a different machine learning framework. Normally you'll have the input features and the labels, right? right now we've got them separate. So we've got images over here and we've got labels over here. My hands aren't inside of the frame. So we've got them separate. We want to combine them so that it represents one sample. So the input features and the labels. So first thing that we're going to do is just check our partition length. So I'm just printing out the length of each one of these partitions. So our training images and labels, we've got 3,720 samples. For testing, we've got 840. And for validation, we've got 720. Kind of crazy, right? So we've gone from having, 90 images to what is that? Well over 4,000, probably approaching 5,000 samples. Kind of crazy. I think it's absolutely amazing. Okay, so that is checking our lengths. Then the next thing that we need to do is actually join these up. So again, I'm just repeating this 3 times for train, test, and val. If you've got a more Pythonic way to do it, let me know, update it, and I'll hook you guys up and we'll push it into the repo. But just know that this does work. So we're going to be doing training, testing, and validation samples. Okay, so what are we doing here? So we're using the zip method to combine these. So we're effectively going to be combining each one of the examples in each one of these data sets. So the zip method effectively allows you to build that type of generator. So train equals tf.dataset.zip. And then to that, inside of parentheses, we're passing our training images and our training labels. Then we're going to shuffle it up. And ideally, you want the shuffle buffer to be bigger than the size of the data set. So we can actually drop this down. We could make this 4,000 over here. 5,000 should be fine for now. I think I had more images when I was building this up. And then we're going to batch it up. So this means that we're going to have each batch is going to be represented as 8 images and 8 labels. So train equals train.batch, and then we're passing 8 to that. And then we're going to prefetch. So this helps eliminate bottlenecks when you're loading and training your data. So train equals train.prefetch 4. And then we're doing pretty much the same thing for our testing partition and our validation partition. So if we go and run these, boom, 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 all things holding equal, we're looking good. So now if we go and run train, and I know there's a lot of data pre-processing, guys. This is just part of the deep learning process. So train.asNumPy_iterator.next, we should now get 8 images, 8 annotations. So if we go and grab the first thing, .shape, should be 8 by 450 by 450 by 3. Or actually by 120, because we've gone and resized it as well. So we've got 8 images by 120 pixels wide by 120 pixels high by 3 channels, because it is a colored image. If we go and type in .1 here, it should return the label. It might not be a NumPy array. That's fine. Yeah, cool. So we've got all of our different classes, and we've now got all of our bounding boxes down here. You can see we've got some 0 samples, so some negative samples over there, looking good. All right, cool. That is our data set now done. Now, before we go on and start doing some deep learning, let's actually go and view these. So we'll grab one sample. So again, you've seen me write this a few times. So train.asNumPy_iterator allows you to loop through all of the different batches. So data_samples equals train.asNumPy_iterator. So if we run that, and then we can grab the next batch. So res equals data_samples. So what we're grabbing from here, .next to grab the next batch. Might take a little while. And then we can actually go and plot it out. So if I go and run this, boom, look at that. So we've actually got our images annotated and augmented. Pretty cool, right? So if we go, let me zoom out a little bit so you can see that a bit better. How cool is that? So if we go and run another sample, look at that. So we've now got a ton of augmented data. And you can see some of them are darker, some of them are lighter, because keep in mind, remember we had a random brightness function inside of our augmentation function. So all of this hard work has led us to this. Looking pretty good though, right? And again, you can keep running the data_samples.next to keep getting the next batch. So that's effectively what I'm doing. Eventually I'll reach the point where I've gone through all the batches and it'll return none. So if you run this too many times, you'll get to the end. In that particular case, just run this again to regenerate or restart the iterator, and then you can go and grab the next batch. So again, can keep running through it. Okay, but that is our data pre-processing now done. So I know we did a absolute ton of stuff in there and wrote a ton of code, or went through a ton of code. So just know we've gone and successfully reviewed our data set and built our image loading function. We've gone and partitioned it. And remember, we did that manually. We've then gone and applied augmentations for our augmentation pipeline. We've then gone and built our augmentation pipeline and generated a ton of data. So we've now got 3,720. Let's zoom in so we can see this a bit better. So we've now got 3,720 examples in our train, 840 in test, and 720 in val. And we've gone and created our final data sets, which we've gone and visualized down here. And this is all just done using matplotlib. So again, we're using subplots and we're drawing a rectangle using OpenCV and then using IMShow to actually visualize the image. Okay, that is our data set now done. Let's jump back on over to our client and see what's next.
So we're on to the fun bit, deep learning. So how are we building this? Well, if you think about it, object detection really has two parts. Classification, so determining what the object is, and that can really be thought of as a binary classification problem, and finding the coordinates for the bounding box. So x1, y1, x2, y2, so on and so forth. Now that second part of the problem is actually a regression problem. Interesting. Yep, so that's exactly what we're going to build. We're going to use a VGG16 base architecture and add on our final prediction layers. One for classification and one for regression in order to do object detection. Sweet, but how do you train it then? I thought the Keras sequential method expects one input and one output and one loss function. You're mostly right. We're actually going to use the functional API for this model. This will allow us to have two different loss functions and combine them in the end, one for the classification model and one for the regression model. The latter will actually be called localization loss, and we'll write this function ourselves. Nice. I guess let's do it then.
Alrighty, just went and had some lunch. It's time to wrap this up. So our client gave me a lunch break. It is time to build our deep learning model. Okay, so I'm going to delve into this now. So step 8, we have, what do we have? 4 steps that we need to do. So we're going to import our layers and our base network. Now, what I mean by base network is this bad boy over here. So let's quickly take a look. I think I got a bunch of extras here. We'll go back through this. So for now, what we're going to do is first up import the model class. So from tensorflow.keras.models, import model. So this is the base or what all of the TensorFlow models are built from, right? Then we're importing a number of layers. And I probably should clean this up, but for now, just know that we're going to import layers. So from tensorflow.keras.layers, actually, let's take a look. I'll clean this up. So on the fly. So we're using input VGG. So I think we can get rid of flatten. Yep, we don't need that. We don't need add. I don't think we've got dropout. Let's clean this up. We don't need that. We don't need relu. Yeah, perfect. All right, cool. I just want to make this super clear for you guys. So you're not looking at this and like, why the hell did he import that? Okay, that's what we're going to import. So from tensorflow.keras.models, import model. So that's our base model class for our layers. So from tensorflow.keras.layers, import input, conv2d, max pooling 2d, dense, and global max pooling 2d. Wait, did we use that? Oh gosh, you guys are going to shoot me. Yeah, we didn't use max pooling. We used global max pooling. Okay. Get rid of that as well. There you go. Nice and simple. Okay, so we've got input conv2d, dense, global max pooling 2. I guess the reason that I've got those layers is as I'm prototyping this for you, I'm like testing out a bunch of stuff and like trying to build specific types of neural networks. So if ever you see stuff in there and you're like, he's got extra things, I'm not using this, that's probably why. Okay, so these are our layers, and then we're going to import VGG16, so this big bad boy. So VGG16 is a huge neural network, or reasonably big neural network that I believe was built for image classification, and it's got a bunch of convolutional neural networks. So that's what VGG16 looks like. The nice thing about Keras is that we can actually pick this up and use it. So we're actually going to cut it off here and pass from this big block over there into our specific regression model. So this has obviously been pre-trained as well. So you can leverage that knowledge inside of that neural network. And this is how it's intended to be used. So let's first up import this. Now, what we need to do is create an instance of VGG. So what we can do is write VGG equals VGG. And this is standard architecture. Actually, good segue. So a lot of the time I get comments on, Nick, how did you design this neural net? How do I pick the number of units? Now, a large part of this is based on research that's out there. So I'll go back and I'll take a look at different types of neural networks and go, hey, they've built it like this. Maybe I can tweak it for these particular sections and get my output. in this particular example, I think I started off with the SSD architecture. So if you've ever seen the TensorFlow object detection course that I've got, then this is the model that we actually used for that. So we used a SSD model for object detection. So, and you can see there that the SSD model is using VGG16. So I was like, why not capitalize off what the greats have done, and we'll use VGG16 as well. And that's exactly what I've done. So, but obviously it's not exactly the same as this. We've gone and tweaked it. So we are going to be using VGG16, and that's the first thing. So VGG, and I'll probably explain a little bit more as to why I've made certain other design decisions as well. But just bear with me for now. I'm going to go into this. So VGG equals VGG16, and then I'm saying include top equals false. So the final couple of layers in VGG16, we don't actually need, because we're going to apply our own. So we don't need all this stuff here, because remember, our object detection model is really two models. It's a classification model and a regression model. The VGG16 model is actually a classification model. So we need to get rid of those final classification layers and sub it for our own final layers, which is exactly what you're going to see in a sec. So VGG equals VGG16, and include top gets rid of those final layers. So we're going to run that. And then we can actually take a look at the VGG model. Keep in mind, if you haven't run this ever before, it's going to take a little while to download. I can't remember. I think it took me like 3 minutes on my net, which is slow as hell. So VGG.summary is going to actually show you what the neural network looks like. And see, the beauty of this is that this is actually a pretty big neural network. So what is it, like 14.7 million parameters? We don't need to go and train this. Obviously, we're going to fine tune it, but this is already giving us a bunch of knowledge inside of our model because it's been built for image classification. And it's already got a number of convolutional neural network layers in there. So you can see we've got a conv2D layer there, which has 64 layers, or 64 kernels. We've got a max pooling layer. So that condenses that information down. Again, conv layers, max pooling, conv layers, max pooling. Now, on the end here, so you can see that we've got none, 512. So effectively what this is going to become is 120, or whatever our original image is. So 120 by 120 by 512. And obviously this might get changed or tweaked a bit depending on what types of inputs and what other transformations have been done. But this is what these nuns represent. So the number of samples plus the, effectively the, width plus height, and then the number of channels. But this is obviously going to get transformed a bunch depending on whether or not the padding is set to same. But just know we're going to be taking a really bulletproof architecture. We're going to be plugging it into our object detection model. So that's the beauty of it. So that's VGG.summary. So again, you can use .summary to get information about a whole bunch of different types of neural networks inside of Keras. So let's build our neural network. So let's run this. So what we've actually gone and done is, let me show you. So first up, what we're doing is we're specifying an input layer. So whenever you're building your neural network, remember you need to have a bunch of inputs and either an output or multiple outputs. So let's start with the top and the bottom first. So our input layer is going to be an input, which is using this input class up here. And this is actually using, I believe this is using the functional API, which gives you a little bit more flexibility. So we're using an input, and our shape is going to be 120 pixels by 120 pixels by 3 pixels. Don't worry about any of this. Now, let's take a look at our outputs. So our outputs are specified over here. So we've got two outputs. We've got a classification output and a regression output. Now, how crazy is that? That matches to what our annotations look like. Remember, we've got one output for our classification. Let's take a look. So if I go and type train.asNumPy iterator.next, and let's go and grab our outputs. Look at that. So we've got a classification output, so 101010, and then we've got some regression outputs, which are 4 different values. Now let's go back and break this down a little bit. So our classification is mapping to class 2, which is class 2 over here. And that particular layer is a dense layer, which has one output. So that means it's going to output one value. And because it has an activation of sigmoid, that means it's going to be a value between 0 and 1. Remember, the activation acts like a modifier to the output of a neural network. So if we take a look at our sigmoid layer, I want sigmoid activation. Actually, that's it. This is what a sigmoid activation looks like. It takes any input and it maps it through to a value between 0. You can see that 0 is the bottom value on our y-axis, and 1. So that's what's going to happen, which just so happens to be 0 and 1 in terms of our classes. Now, our dense layer is going to be over here. So if we take a look at our regression layer, our second output is going to be regress 2, which is regress 2. That particular layer has 4 outputs, which also has an activation of sigmoid. We've got 4 outputs in our labels. And remember, they're scaled between 0 and 1 because we've gone and divided it by the dimensions of our image. That is effectively the crux of building neural networks. Focus on the input and getting to the output, and then you can tweak what happens in the middle. So you can tweak the hidden layers. Now, in terms of our hidden layers, let's actually go and take a look at what's happening in the middle of our neural network now. So once we've taken in our input of 120 pixels by 120 by 3, then we're taking that input layer and we're passing it through to our VGG16 layer. So you can see here, we're instantiating VGG as VGG16, and we're specifying include top equal to false because we want to drop off those final layers. To that, we're going to be passing through our input layer. So you can see that what we're actually doing is we're doing 2 things here. We're creating the layer and we're telling the layer what we're going to be passing through to it from our neural network. So effectively, we're going, this is our input layer goes to our VGG layer, and then our VGG layer is going to be put into something else. This is how the neural network is stacked up. Right, so input layer VGG, and then here we've actually got effectively two different output heads or prediction heads. That's what people typically refer to the final outputs of a neural network, right? So we've got 2 prediction heads. This first prediction head over here is actually our classification model. And what we're doing is we're first up condensing all of the information from our VGG layer using the global max pooling 2D layer. Think of this as taking or looking across all of the different channels in our VGG output and condensing it and only returning the max values. So what will end up happening is that rather than having all of the dimensions from this 512 layer or this layer here, we're effectively just going to get 512 values back. And these are going to be the max values out of each one of these channels across the board. So we're then going to take that output, which is now stored in a value called F1, and we're going to be passing that through to a fully connected layer. So that F1 value, which represents the output from our VGG16 layer, goes to a dense layer, which has 2048 units with an activation of ReLU. That value, which is now stored inside of class 1, gets passed to our final classification layer, which is class 2. I've just called it class 2 because classification second layer, you sort of get the idea. And remember, that's got the 1 output because it maps back down to here. Now, likewise, we've got our regression model here. So think of this as our bounding box model. This is again going to take in our VGG outputs. You can see that there. And we're again going to apply max pooling 2D. Then that output, which is now stored inside of F2, goes to a regression. Oh, this should actually be F2 down here. That's actually an error. So F2 comes from over here, gets passed into this layer. So that now means that we are going to be taking our VGG outputs, passing it through to F2. And what we'll get out of this is regression 1 is then going to be represented as a dense layer of 2048 units with an activation of ReLU. And then that regress 1 value goes to our final regression layer, which means inside of regression 2, we've got a dense layer with 4 units and an activation of sigmoid, which maps through to our bounding box coordinates down here. So all in all, think about that as this. So we've got an input, which goes through a massive classification model, and then those 2 outputs get broken down into a classification model and a bounding box model. And then we combine it all together using the model API down here. So model is over there. To that model, we basically pass through what our inputs are going to be, which is our input layer, and what our outputs are going to be, which is going to be the class 2 outputs of the class 2 model and outputs of the regress 2 layer. Pretty cool, right? And then we return that back. So now if we run this, we've effectively we've created a function which instantiates our model. So we can actually go and create an instance of it now, which is what we'll do inside of 8.4. So we can use face tracker equals build underscore model. So we're actually going to be running this build model function because remember that returns our neural network. And then we can actually take a look at that neural network. So let's disable scrolling. All right, so let's take a look at this. So we've got our input layer over here, which is 120 by 120 by 3. That gets passed through to our VGG16 layer, which remember is going to be none, and then 512, but it's really getting this output over here. And then our global max pooling layer is reducing the outputs of this VGG16 layer, rather than going none, none, 512, it goes to 512 outputs. So based on each sample. These two values then get passed to our two dense layers. So over here, this first one over here is the output from our classification model. So that then gets passed to dense one, which gives us our classification output, which is just one value. This dense layer over here, you can actually specify names for this, so it's a lot clearer which layer maps to which, but I haven't done it here. So dense 2 is going to be 2048 values, which again maps to 4 bounding box values. All in all, our neural network is 16.8 million parameters, so quite big. Okay, that is our neural network now done. Now just remember, like when I'm actually designing these, I'm thinking about what's been done in the past, can we leverage that information, and what does our final output need to look like? That's the core crux of how to build these. Okay, that's our summary taken a look at. We've taken a look at that. So we can now go and grab a sample out of our training pipeline. And that is going to unpack X. So X will be our images, Y will be our labels. We can view that. So X, again, images, Y, labels. Cool. Now we can take a look at X.shape. So again, 8 by 120 by 120. We can take a look and actually pass this through to our face tracker model. So face tracker.predict, and we're passing through our images. So ideally what we'll get out of that is our classes and our coordinates. Right now we haven't trained it, so it's going to be crap, but this is ideally how you're going to use it in the end. If I go and run that now, we should get some predictions. So that might take a little second. And if we go and print it out, take a look. So we're now getting all of our classification outputs as this first value and all of our coordinate values as this second value. So once we go and train, it should learn how to estimate these and return values which are closer to the actual outcomes, or the closer classification outputs and the closer bounding box outputs. So that is step 8 now done. So we've actually gone and now successfully built our neural network. But keep in mind, because we've got 2 outputs, we actually need to do a little bit of tweaking when we go and train, because we need a specific loss function for our classification model and a specific one for our regression model. So that's what we'll do in a sec. But just know we've now gone and successfully built our neural network. We are now up to step 9, defining our losses. So first up, or our losses and our optimizer. First up, what we're going to do is we are going to specify what our learning rate decay is going to be. And again, I didn't get too fancy on this. I think I actually found out how to calculate this from Stack Overflow. But basically, what we're specifying here is how to decrease the learning rate in such a way that we're 75% of the original learning rate after each epoch. So this means that we'll slow down the learning. So ideally, we don't overfit and we don't blow out our gradients. First thing we need to work out is how many batches we've got within our training data set. So if I type in len, train, we have 465. So what we need to do is replace this value here. So batches per epoch should be 465. We could actually even just set it to this, right? So that way it's correct each time. And this is going to specify our learning rate. And then what we're going to do is set up our optimizer. So we're going to be using the Atom optimizer. So think about it, your optimizer is working out how to go and apply gradients and effectively apply backprop across our neural network. So opt equals tf.keras.optimizers.atom. And then to that, we're going to pass through our learning rate, which is going to be 0.001. And then our decay is going to be this decay value over here. So if I actually show you this, LR decay, so that is effectively how much our learning rate is going to drop each time we've gone through one particular epoch. Again, you could just plug in a value here as well if you wanted to, if you didn't want to go and do this calc. Okay, so then what we're going to do is we're going to create our localization loss. So let me actually show you what this looks like. So localization loss. I saw a really good formula for it. I think it was this one. Yeah, take a look. So basically what we're actually calculating here is this component. So this bit and this bit. Now we're not square rooting it. That's perfectly fine. So effectively what we're doing is we are getting our distance between our actual coordinate and our predicted coordinate. So this is what this line over here is doing. So what we're doing is we're getting our y true value, which is going to be our first coordinate minus our second coordinate. And this is going to do our x and y at the same time. So we're then going and squaring the difference and we're reducing the sum. So we're effectively summing it all back up together. And that gives us our delta value over here. Then we're calculating our actual height of the box, the actual width of the box, the predicted height of the box, and the predicted width of the box. And we're doing pretty much the same thing that you're seeing down here. So we're getting the true width minus the predicted width, we're squaring it. We're then getting the true height minus the predicted height, we're squaring it. We're adding both of those two values together, so you can see the plus there. And then we're using tf.reduceSum to reduce that value into a single outcome, which gives us the value delta size. So the difference between the coordinates is stored inside of a variable called delta coord. So delta coord plus delta size gives us our localization loss, which is what we're returning down here. So return delta coord plus delta size. So if I go and run that, and then we go and test it out, or we actually go and create variables for those. So classification loss is then going to be passed through to our training pipeline, and regression loss is going to be set to our localization loss. So the classification loss, keep in mind, is going to be binary cross entropy because it's just a classification problem, right? We don't need to get fancy there, but we could if we wanted to. And then we're going to test it out. So our localization loss, we can pass through our bounding box coordinates. So we're going to test against y1, which is what we had from over here. And we're going to pass through our coordinates. That looks okay. So if we type in .numpy, we get the actual value, which is going to be 6.5 to begin with. But again, we haven't trained our neural network, so it's going to be pretty crappy to begin with. Okay, and we can test out classification loss, which is going to be binary cross entropy. So in this particular case, it's 0.584. And again, to get that value, you can just type in .numpy, boom. Okay, that's looking good. And we don't have this is regression loss, so it's going to effectively be the same as localization loss, but boom, 6.05. Okay, that is step 9 now done. So we've now gone and defined our optimizer. We've gone and created our localization loss and classification loss, and we've also gone and tested out those metrics. Now what we need to do is actually train our neural network. But before we do that, we actually need to create a training pipeline. So for that, we're going to create this class over here. Let me zoom out a bit so you can see it. So what we've got is the base model class. So we're creating a new class called face tracker, and to that we're passing through model from over here. And then let's actually take a look. So whenever you're creating subclassing the model class from Keras, there's a couple of things that you need to have. So you need to have an init method, a compile method, a train step method, and a call method. So let me explain what each of these does. So the init method is where you can pass through your initial parameters. So in this particular case, we're actually passing through our pre-built neural network, which is the eye tracker model. Actually, it shouldn't be eye tracker. That's fine. I called it eye tracker previously. It'll still work, which is actually the face tracker model from over here. So remember, we instantiated face tracker here. So face tracker equals build model, which is creating an instance of this deep learning model over here. Then what we're doing is we're passing that through to our init method. I've called it eye tracker, it could be anything, but we're setting that equal to self.model. So self.model equals eye tracker. Then we're compiling it. So remember, whenever you build a Keras neural network, you typically create the network, set self.compile, and to your compile method, you pass through your loss and your optimizer. That's exactly what we're doing here. So def compile, and then we're passing through our optimizer, our classification loss, and our localization loss. And we're setting those variables over here as class variables. So we're able to, or class attributes. So we're actually able to get those out. So before we're doing that though, we're running super.compile. So because this is a subclass model, we're compiling this model as well. We're then setting all of these loss metrics. So self.classification loss equals class loss from up here. Self.localization loss or LL loss equals localization loss from up here. Self.opt equals opt from up here. Then this is where the magic happens. So this train step is where a lot of the hardcore stuff actually happens and where we actually train our neural network. So let's get ready to explain this. So train step is going to take in one batch of data and it's going to train on that batch of data. So that's the first thing to know. So first thing we do is we get that batch of data and we unpack it into its X and Y values. What we then do is we then tell Keras to actually start calculating each of the different functions which are being applied to this information as we go and train our model, or as we go and do stuff within our model. So what we do is we first up make a prediction from our model. So we run self.model, which remember is taking in our face tracker model. It says eye tracker here, but it's effectively taking in our face tracker model. And we're passing through our X values, which remember are our pre-processed images. And we're setting training equals to true because if we've got any specific layers which perform differently during training to inference, it's going to activate those layers now. Now remember, our model returns our classes and our coordinates, so we can then take those classes and coordinates and pass them through their respective loss functions. So we get batch class loss equals self.c loss, which is really just our classification loss. And we're passing through our classification values. Remember the ones or zeros. And we're passing through the true ones or zeros, which we're getting from over here. No, we're passing through the predicted ones or zeros. So y0 is it going to be y true, classes is going to be y pred. So over here, this is y true, y pred. Then our batch localization loss. Sorry, my throat is dying over now. Let's grab a glass of water. This is always the problem with these huge tutorials. By the end, I'm like absolutely dead. All right, batch localization loss equals self.ll loss. And then to that, we're passing through y true, and we're passing through our coordinates. Now, I noticed when I was building this up that I had to cast the value to be a TF float 32. So you can see that I'm casting that value there. Just know it'll work. It's just something that I had to do to get the loss function to work appropriately. So we've got batch class loss, batch localization loss. We're then going to add those together to get one loss metric. So total loss equals batch underscore localization loss multiplied by 50% of the class loss. That's just something that I chose. You could tweak that if you wanted to, but I found that tended to work. And then we're actually going to calculate the gradients. So this is really important when you're using a custom training step. So you calculate the gradients and then you use your optimizer to go and apply them. So with tf.gradient tape as tape, so this is actually starts calculating all of the operations that are happening inside of our neural network. And then we can actually use tape.gradient to actually go and get each one of those gradients or calculate those gradients. So grad equals tape.gradient, and then to that we're going to pass through total loss. So we're actually calculating the gradients with respect to our loss function. And then we're passing that through to self.model.trainable variables. So what you'll actually get out of this is all of the gradients for each one of those variables with respect to that loss function. And then we go and do gradient descent. So optimizer.apply gradients, and what we're going to do is loop through each one of these gradients and apply one step of gradient descent. So effectively, we should be optimizing closer towards minimizing that loss. So zip, grad, and then to that, we're going to pass through each one of the trainable variables. So self.model. My head blocking that. It is self.model.trainable variables. So I wanted to explain this in a little bit more detail, right? So because this is really important. So train step is effectively going to give you that or perform that training. So remember, train step is going to be what actually trains our neural network. And if you think about it, there's a couple of key steps. So first off, you trigger that monitoring. So TensorFlow is going to start calculating all the operations. You make a prediction, you calculate the loss, you then go and calculate the gradients, and then you go and apply backprops and apply gradient descent against all of those different variables. So that in a nutshell is what's happening there. And the reason that we had to do this is because remember, we've effectively got two prediction heads. We've got classification and we've got our regression model, which gives us our bounding box coordinates. And then what we're doing is we're returning those losses. So we're returning total loss, batch class loss, and batch regress loss. And so what we'll actually get back is a dictionary. So when we go and run our training step, we can see the progress. Now, our test step actually allows us to is actually triggered whenever we pass through our validation data set. And this is almost identical to our train step. The only difference is that we're not actually going and applying backprop here. We're just going and calculating our total loss, batch class loss, and batch regress loss over there. So if you look at this versus this, the core difference is that we don't have the tf.gradient step tracking, and we don't actually have these two lines here, which are actually going and calculating the gradients and doing backprop. So it just still gives you the ability to go and validate your model. And then we've got def.call. I don't think we're actually going to use this, but if ever you wanted to use .predict for a model, you need to implement def.call. Okay, so that is our training step now created. So we can actually go and run that. And again, all this code is going to be available via GitHub. So if you want to go into it into a ton more detail, if you've got questions you want to ask me, hit me up in the comments below when my voice is back. Okay, so let's zoom back in. So that's our neural network now defined, or our training step now defined. So what we now need to do is just set it up. So we're going to subclass our model. So model equals face tracker, which is this subclass over here. And then to that, we're going to be passing through the neural network that we set up just before, which had our VGG layer. So which had this over here. This could be named anything. It could be named custom model, blah, 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 whatever you wanted, or OD model, for example. And then all you do is you'd pass through OD model or face tracker model, or eye tracker model, or whatever you wanted to over here. So just know that the model at the top maps into this model over here to give us our custom training step. So we've just gone and created that. We can then go and compile it. And to our compiler, we have not instantiated our optimizer. So let's go up to here. My mouse has just died. There we go. We're back. Okay. So let's go back up to here. We didn't actually run our optimizer, so we need to run that cell. And then if we go back down here, when we go and compile, we are going to be passing through our optimizer, our class loss, and our regression loss. If we go and run that, that has gone and compiled successfully. Then we can train. Okay, so we're going to specify a log directory, and this is where our TensorBoard model will log out to. So if we go and run that, and then I go and run this line, this actually creates a TensorBoard callback. So if you wanted to go and review your model performance after you've actually gone and trained, you'll actually be able to go into here. It'll create a TensorBoard log directory, which you can pick up and go and review. If you want more details on that, hit me up in the comments below. Okay, but for now, this is the magic line. So let's take a look. So model.fit is going to call this model over here, and it's going to, remember, fit is going to trigger our train step. And if we've gone and passed through validation data, it's going to trigger our test step. So hist equals model.fit, and then to that, we're passing through our training data. And if you wanted to pass through a smaller amount of data, you can type in .take to grab a smaller batch. We're going to pass through everything, so we'll get rid of that. We're going to specify how long we want to train for. So epochs equals 40. So this means we're going to train for 40 epochs. And then we're going to specify our validation data. We're jumping over onto my trackpad, which is kicking off weird stuff happening. So let's, are we zoomed out? Yeah. That's zoomed up. All right, cool. That's looking good. All right, so what are we doing? So we're going to then pass through validation data, which is going to be our validation partition, which we set up right up at the start. And then we're going to specify our callbacks equals to this TensorBoard callback, which again is purely optional, but I just do it just as backup if ever I wanted to come back and take a look at my training data. Now, because we've specified that we're going to save this model to a variable called hist, this means that we'll actually be able to get our training history. So when we go and run the fit model and assign the outputs of that to a variable, we're actually able to get our history back, which is right what we'll do down here. We'll actually plot out our performance. Okay. That is our fit model. So assuming we've gone and done everything successfully, if we go and run this line now, we should kick off training. So let's run this and see how we go. And we've got errors. Batch regress loss is not defined. So what have we done there? So batch regress loss, have we not gone and this should be, so batch localization, it really should be localization loss, not regress loss. I think, where is it failing? Let's just quickly double check. Looks like we've got a bug there. So it's failing in train step. Do we have regress loss here? So self.ll loss. Oh, it's in here. So this should be, so batch localization loss should be that there. That should be that updated there. And this should be that there. Looks like we had a couple of bugs there. So batch localization loss, batch localization loss. It looks like we just didn't update this training step. Okay, let's try that again. Cross our fingers. Okay, so we're training. So you can see that our model is running through all of the different batches inside of our training epoch. So you can see it's 465. That's our total loss. That's our classification loss. And that is our regression loss, or effectively what our bounding box regression loss model looks like. Now, ideally, you want to see a smooth reduction in all of those loss metrics. And you ideally want to, looks like there's a massive disparity between our regression, validation regression loss and our base regression loss. So again, it might be an indication, well, we've got a lot of data, so it might make sense. And our validation partition is pretty small, but I don't know. Let's wait for this to finish training and then we'll actually be able to see how this is performing. Let's give it a couple of epochs and see. Okay, that looks a little bit more reasonable. So our regression loss is pretty close to our val regression loss. Actually, let me explain this. So this is our total loss metric, and that's going to be, remember, our batch localization loss plus our batch class loss multiplied by 0.5. And then we've got our val metrics as well. Sorry, I'm losing my voice now. So this is val total loss over here. Let me zoom out, actually zoom in. All right, that's a bit easier. So total loss, class loss, regression loss, and then we've got where they're prefixed with val. That's what we've gone and done on our validation partition. So val total loss, val class loss, val regression loss. So what you want to see is that all of these metrics reduce progressively and pretty consistently with each other. So you don't want to see val regression loss dump massively or spike massively. Likewise, you don't want to see classification loss dump massively or spike massively. you all want them to be reducing pretty consistently. So you can see that, let's take a look. So our val regression loss is 0.543. Our base regression loss is 0.543. Our val regression loss is 0.0166. So that's looking okay. Ideally, you don't want to see one drop way too much more than the other. You don't want to see stuff just going crazy. So what we'll do is we're going to review this in a lot more detail once we go and plot our performance down here inside of 10.3. So let's let that finish training, and then I'll be able to walk you through what that's looking like. So we're up to epoch 6 now. Total loss is at 0.0394. So that value that you can see there. And let me zoom in so you can see this. So total loss is that value there, and val total loss is that value there. So we've got a little bit of a discrepancy, or it's not discrepancy, this is part of training. So 0.0394 and 0.0713. Now, if we break that down, classification loss on the training partition is 0.0148. Val classification loss is 0.038. So that must mean the regression loss is diverging. So if we go and take a look, val regression loss is 0.0695. And on the training partition, it's 0.0321. So let's keep watching this and see how we go. So it looks like val regression loss is bumping up a little bit. Okay, that looks a little bit more consistent. So val regress is 0.018. Train regress will be 0.0117. So ideally, you want them to both be decreasing at a consistent rate. You might get spikes occasionally, but it shouldn't spike massively and then stay massively out of whack. All right, so let's let that train, and then we'll be right back and we'll be able to see how this is actually performed. So again, we're training, we're getting stuff done. All right, so that is our deep neural network that is finished training. Now, it'll be interesting to see what performance looks like, because I saw validation regression loss bouncing up and down, but we shall soon see. So at least the nice thing that we can do is we can at least go to history and type in .history, and we can actually get all of our loss metrics and see how this was actually performing. So training performance looks like it was reducing pretty consistently, but I think we had some, or at least from the validation partition, we had a little bit of bouncing up and down. Now this might be caused by a whole bunch of things, because you can see you got a spike there. Possibly there was some weird data, some weird annotations, or some crappy annotations. I don't know. We'll actually find out soon. So if we actually go and visualize this performance, we can actually go, I've got the exact same thing written there. We can actually take a look at his.history to get that history back. And that's because we've gone and saved model.fit to the variable history. So that actually allows us to get that performance. But rather than look at it like this, it's probably easier to actually plot it out. Let me zoom in. We're a bit too zoomed in there. So if we actually go and plot this, so this loss will actually plot the total loss, the validation loss, or the total loss, the validation total loss, the classification loss, the validation classification loss, the regression loss, and the validation regression loss. Wow, I'm really losing my voice. So if we go and run this, let's actually take a look. See, so you can see regression loss was bouncing up and down. Now this is a little bit concerning, but maybe we've got some weird data in that validation partition, who knows. So you can see classification loss performed pretty perfectly, but it looks like we had some weird stuff happening in the validation partition. Possibly, I'm thinking maybe there was some weird annotations or something. Let's actually go and take a look. What's our validation data look like? So we go and take a look at our images. I don't know, maybe it threw up on this, or like it wasn't too happy with this particular image here. Let's actually test it out. I mean, let's jump back on over to our client and we'll actually be able to see what this performance looks like to begin with.
All right, final stage, making predictions. You got it. We're going to do this on our test set, but also in real time to evaluate performance. Nice. Let's wrap this up.
Alrighty, so we're in the end game now. So making some predictions. So first things first, let's go and make some predictions on our test set. So to do this, we can write test_data equals test.asNumPy iterator. So this will set up an iterator. Seen this a bunch of times. We can then go and grab the next batch. So test_sample equals test_data.next. So this is just going to grab one batch of data. And remember, it's going to be 8 examples. And then we can go and run a prediction. So we can use our face tracker model. So face tracker.predict, and we can pass through the test sample. Now, remember, we just want the X values, not the label. So we can actually type in y equals test data.next and just pass through X here, right? it'll do the exact same thing. Now we can take a look at these predictions using this plot. So this is actually going to predict or only plot it out if the classification loss is over 0.5. And if it is, then it'll actually go and draw the rectangle. Now this is exactly the same as the way that we drew the annotations towards the start after we'd done the augmentation, but let's actually take a look. Okay, so this is performing absolutely terribly. So something's gone terribly wrong. So you can see there that we are not picking up our faces whatsoever. So this is a problem. Now, I'm wondering if whether or not we changed that final output layer or that final connection over here had an issue. So we had this set to F. No, we had, what did we have? So we had this connection set to hook into F2 over here. But previously when I tested it out, F1 had seemed to work. I wonder if changing that had influenced the model. Let's actually quickly double check our annotations first. So if we go and grab something out of the, let's keep going through and take a look at our training sample. So if we notice that we've got weird images here, I'm wondering whether or not it's the architecture. So if we go and run that, that looks okay. That looks okay. That looks okay. Oh, we need to get the next one. Those annotations look fine. They look fine. Let's just quickly take a look at, we don't have, no, we've got the annotations here. So if we take the sample cohorts, no, we want sample classes. So res 1, 0. Yeah, so these all effectively are labeled correctly. So 1111, that's fine. I really wonder if changing the architecture here has screwed it up. Because previously I must have gone and trained it with F1 hooked in. So this particular dense layer connected directly to the single global max pooling layer. Now, let's see if changing this improves our model. So we could actually get rid of this layer because F1, or this particular regress 1 layer is hooked into F1, which is this over there. So we could actually take this out and say it's almost like that. Now, I wonder if that gives the models more connectivity. I don't know. Let's see. So if we go and run that, we go and rebuild our model. It's got 16.8 mil params, still fine. There's nothing else that we've changed. Kind of weird that we're getting such bad performance. Learning rate's fine. We've gone and done anything weird over here. So let's take a look at our loss metrics again. So batch localization loss equals that, which equals self dot localization loss. That's fine. Classification loss. And we're returning, total loss goes to there. Probably good that you see me debugging one of these, because then you're like, well, this is how to actually build these up and fix stuff when stuff goes wrong. So batch localization loss gets passed to there. That's okay. Batch localization loss, that's okay. So we're just double checking that all loss metrics are assigned correctly. Let's go and kick this off again. But let's train for a little less now. So remember we only trained on 10, I don't know, maybe. Let's go and train on a smaller batch and let's drop the epochs to 10. Let's see what happens now. So this is obviously going to allow us to train faster, but it's not capitalizing on all the data. Okay, so regression loss, 0.8246. Only thing I'm thinking is that maybe we've got bad data and stuff is getting thrown out. Okay, so what do we have? So regression loss, those are decreasing pretty consistently. Val regression loss, that's okay. This is still decreasing in line, but is bumped up now. Weird. Okay, so I'm just double checking that regression loss is decreasing in line with the val regression loss is decreasing in line with regression loss. If it's not, then maybe we've got a problem. Okay, so that's gone up again. I wonder if we've got issues. Okay, so this has gone down massively now. And regression loss has gone up. Gone down, okay. This has gone down, this has gone up. We've got issues, I think. Okay, so they've kind of converged. I don't know. Let's take a look at our history. That's looking better. Right, so at least our classification loss is dropping, our regression loss is dropping. What do our predictions look like? Okay, so we're getting weird bounding boxes over here. Why are we getting two bounding boxes? Okay, this one at least looks okay. Let's actually go and train. I wonder if there's weird data. Let's give it more data and see if that throws it out. Actually, let's train for longer to begin with. So let's go for, I don't know, 40 epochs. Zero 0.01, 0.04. I think something's going wrong. Let's stop this. Hold on. Let's go and plot this out again. This will be from the last set, so that's not relevant just yet. Something's broken. We shouldn't even be rendering two boxes. Go and get the next set of data. Yeah, something has clearly gone wrong because we really just shouldn't be rendering out two sets of data. Hold on, test data. What are we doing here? Okay, so then we need to render on... Wait, we changed this. This should be test sample over here. And then let's pass through test sample 1, 0. Okay, so maybe we went and screwed up the rendering. Hold on. So maybe we are rendering okay. Okay, so that's picking that up. It's not picking up anything there. Let's go and run through another sample. Okay, so maybe the model has been working and we've just been rendering it incorrectly. I think that's what's actually gone wrong because we went and changed this to XY. Let's just keep running through the rest of the sample data. So that looks okay. That looks okay. That looks okay. That looks okay. All right, so maybe we aren't so bad. Okay. Phew. I think the model maybe had been working, but we've gone and screwed up the visualization. I need to validate this because I'm not confident that we needed to go and change this. Let's just go put this back because I want to go and test it out properly. So maybe it's the viz that we screwed up and not necessarily the model itself. So let's go and set this equal to F2, cut this, put that back there. I'll include the final code anyway in the GitHub repo. So we went and reconnected this regression layer back to this F1 layer, but I'm going to connect it back to this global max pooling layer to see if that was truly the issue or whether or not we just screwed up the visualization. I've got a feeling it was the latter. So let's go and redefine that. We're going to redefine our neural network. That's fine. We're going to recompile. Let's give it all of the data back. So we're just going to drop the dot take and let's give it, I don't know, let's train it for like 10 epochs. We won't wait that long. Let's see what our history looks like. We'll be right back. We'll see if that was the bug.
A little longer than a few minutes later.
Okay, so I've gone and retrained it for the 10 epochs. Now, again, we did have one big spike here for our validation regression loss. So if we go and take a look at our history again and our plot, so you can definitely see that there was a massive spike. But all in all, it doesn't look too bad. So it looks like we've kind of been steady in terms of regression loss and validation regression loss. Though we do have that big spike, which is a little bit concerning. But we can go and take a look at our data now. So all we've gone and done is I think we went and screwed up the visualization here because we had X, Y, which meant that we didn't actually go and update when we went and rendered the image over here, which would be sample image. So this really should have been extracting the sample image here. So my screw up might have actually gone and messed up the code here. So if we just go and leave this as test sample, let's go and take a look. Okay, that is predicting faces accurately there. Blocked out our face there. Let's go and make some other predictions. We might be okay, guys. Let's go and print this out. So that sort of reassures the fact that it wasn't the neural network architecture which was out over here. It might have just been the fact that we screwed up the visualization, or I screwed up the visual. I'll take full responsibility. I went and screwed it up, but that's fine. At least you can see what happens when you're building these types of models. Okay, so we've gone and successfully classified our bounding boxes. Let's go and take a look at some other examples. It's looking good, guys. It's looking okay. And right, we can, let's say, for example, you wanted to increase the confidence of a face being in the scene, you could actually increase this value here. So I could set it to 0.9. Still looks like we're picking up faces, right? So the classifier is really, really good in this as well. But it looks like it's not classifying our face when we cover our face. So we're looking okay. So predictions look all right. So again, if you do notice these spikes, I mean, a one-off spike every now and then isn't the worst case scenario, because keep in mind, we do have less data in our validation partition versus our training partition. So it may be more susceptible to changes in the weights. But if you start getting massive amounts of variability, or you just start to see them completely diverging, then you know that you've probably got an overfitting error. But in this case, only retraining, like we went and retrained for 10 epochs, and that seemed to be okay. The real test will be when we actually go and test this with real-time detection. But for now, let's actually go and save this model. So I'm going to import the load model method. So from tensorflow.keras.models, import load model. And then we can go and save the face tracker model. So facetracker.save, and we're going to save it to facetracker.h5. So you can see that we should now have in a second, we've got a facetracker.h5 file. So let me zoom in so you can see it. So you can see that we've now got that there. And if we go and reload it, we should be good. So if you wanted to go and reload it into a different app, that's how you'd be doing it down here. Now we can go and try this out on real-time face detection. So, okay, what we're doing here is we are effectively capturing our video frame. We're then cutting it down to be 450 by 450 pixels, because that's our augmented size. We convert it from BGR to RGB because OpenCV reads it in as BGR. We need it to be RGB for TensorFlow. We then resize it to be 120 by 120 pixels and divide it by 255 to scale it down. And then we pass it to our facetracker.predict method. And then all this down here is really just about rendering. So if you wanted to increase the rectangle size or color, it's really just a matter of changing these over here. So this over here controls the main rectangle. This over here controls the what's called the label rectangle. I know I always get questions on like, how do I increase font size? This over here controls the text rendered. So if you wanted to go and change the font face, it'll be this. If you wanted to change the font color, it'll be this. I think font size, font width, the positioning is controlled by this tuple over here. So let's go and test this out. So I'm very curious to see how this performs in real time. So let's drop this. And I've closed a lot of the blinds in the apartment, so it might be a little bit dark in the background. I don't know. We'll see how it performs. But if I go and run this now, we should get a pop-up. Okay, so what's happened? So we are not picking up our video capture device. That's because we need to change this to... All right, let me explain this. So you can see it says type none-type object is non-subscriptable. That is because it's probably not able to actually get a capture from our video camera. Now keep in mind, when we initially captured our frames, it was from up here and we had our video capture device set to 1. So we've got to change that down there as well to make sure we're pulling from the same camera both times. So if I change this to 1, if you get that type of error, just double check that you're picking up the right video camera as well. Just key thing to keep in mind. We're running this. This is the final test, the final countdown. Let's see if this works. Oh my gosh, guys, take a look at that. We built it. It's picking up my face. Face. So this is a custom object detection model working completely from scratch, guys. I know this took a while to get to and it was a really long tutorial, but that's what's possible. So we went and built it completely from scratch using TensorFlow and object detect. Let's cover our face, see if this takes it away. Take a look at that. So it's no longer picking up our face. 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 But you could use this just for about anything, right? But like if you wanted to go and I don't know, do number plate detection, or if you wanted to, I don't know, capture different cars, you could do that. But like, this is so powerful. This is just the beginning, but it at least shows you that we're able to build a real-time object detection model and one that works on custom data sets using deep learning and completely from scratch. Now, let me take down or open up the blinds to see if it works under different conditions, right? What about if we turned off the recording lights? Still picking up my face, guys. Look how dark I am in the... How good is that though? It's still working, pretty resilient. Lights back on. So even with really bright, like, I mean, this has got autofocus on the camera over here, or auto brightness. So you can see it's gone a little bit crazy, but take a look at that, guys. Picking up a face. If I go down, disappears. Boom. I can't get over this. How awesome is that? So, I mean, we had a little bit of trouble with the rendering, but apart from that, it wasn't too bad to actually get to this. A lot of pre-processing, but that sort of comes with the territory when you're doing deep learning. How awesome is that, guys? So real-time face detection model working pretty well, if I do say so myself. Again, you could add more data. So in the end, let's quickly go through what went wrong there, because I think that's important. Let's do a quick, what do you call it? Post-mortem. I've just opened up the blinds as well, just to see what it works on, like what it looks like under different lighting conditions. I think it still works okay, guys. Like, that's tracking my face pretty well, and it's pretty quick. Like, just, it's working. Can move the mic, still works. Oh my God, this is so good. Like, I've wanted to do this ever since I started deep learning. I'm so happy. How good is that? Oh, I'm going to be playing with this all night. Who knows what I'll be building. All right. Oh, it even works with the green screen, guys. Oh, come on. As if that's not awesome. Keep in mind, we didn't even give it any green screen samples, so it's still able to pick up our face pretty well. That is nuts. Okay, post-mortem though. So what actually went wrong here? So I think I'm keeping this up here just to reiterate how awesome I think this is. So what went wrong? So the key, I think the model itself trained okay. So when we were actually training this, we were perfectly fine. It's just that when we went and visualized it, that screwing up this. So if I went and wrote X, Y, what clicked for me is when it started rendering multiple boxes. This is a single object detection model. So we start to see multiple boxes. Something has either gone wrong with the predictions or something has gone wrong with the rendering. So if I go and do this, right, we're going to start to see multiple boxes or duplicate boxes. Oh, this code is still running. We've got to stop this code in order for this to run. So I'm just going to hit Q now. All right, so we're going to run it once. Now, if I go and do it again, let's get another sample. Another sample. It's not happening. Oh, well, it's got to be something weird's gone wrong. Oh no, it's because we had X here. Hold on. There we go. All right. So the fact that we're getting multiple boxes, so you can see that one there, that's a dead giveaway that something has gone horribly wrong. So you can see that that indicates that something has gone really, really bad, but it's typically going to be something to do with the actual architecture, or it's going to be something to do with the rendering. So either the machine learning model or the deep learning model is outputting incorrectly, or we're now rendering incorrectly. You can see here, as soon as we unscrew this, so we're going to reset it back to test sample. And test sample 0. Let's go back. Boom, it's working again. So we didn't need to go and change the deep learning architecture. We didn't need to go and move around those layers. I think it's okay, guys. This is working pretty well. Let's go and test it once more. So if we go and run our real-time detection test. go. So if you get that little pop up and it closes, just rerun it again. Sometimes it has to reset the video capture. Take a look, guys. Face. Oh my God. I'm so happy. This is absolutely amazing. That brings this tutorial to an end. I know it's been a long one, but we've gone through an absolute ton of stuff. And the final code, including all the things that I tweaked inside of this tutorial, are going to be available on GitHub. I'll make sure to update it right after this, so you got it. But that is it in a nutshell. We've gone and effectively built our own object detection model that does face detection. Hopefully you've enjoyed this. Let's quickly recap what we did in that last segment. So we went and built our deep neural network. We realized that it wasn't an issue with the neural network itself, but I showed you how to go and double check that. So if you wanted to go and change layers, you can move them around. They've got to be the same shape in terms of the output or linear algebra rules applied. We then went and made some real-time detections. We defined our localization loss. We defined our training steps. I explained the custom training step that we went and did, as well as training, how to go and debug, what to look for when you're training. So again, big spikes, one off might be okay. If you start to see huge amounts of divergence, you got to go and double check your data, see whether or not you need to apply regularization, whether or not it's a complete architecture redesign. But in our particular case, what do we end up with? So our final validation regression loss was 0.025. Our total loss overall was 0.065. Our total validation loss was 0.0297. But all in all, it seems to be working pretty well. Again, we could add more data. We could do a whole bunch of additional things. But on that note, that about does wrap this up. Do check the GitHub for the updated code. Thanks again for tuning in, guys. Peace.
Thanks so much for tuning in, guys. Hopefully you enjoyed this video. If you did, be sure to give it a big thumbs up, hit subscribe, and tick that bell, and let me know how you went with this. I did put in a ton of effort to be able to build up this full flow, ideally from scratch and really with minimal dependency. So let me know how you went with it. Thanks again for tuning in. Peace.